right. I've done reading. I have read things that would make your milk curdle in its juice cup. I've read all kinds of stuff about op amps and some circuits that I want to try. See if we can't make a differential signal, and then also do a little bit more with transconductance, because that's apparently a facet of what we're doing here. And it'll help me to understand the M303 a little bit more, in addition to all kinds of other stuff. I am tired, though. I didn't sleep well last night. I just had a night. I fell asleep at my desk, so I feel like I fell asleep at my desk. It's unfortunate. Unfortunate. Got all garbage out, though. At least cleaned up the shop somewhat. Still getting completely choked by this clutter. This is very cluttery over here. So we should clean this up a little bit. I kind of want a cleaner workplace for today. Get the 303s moved aside. Well, we can push this stuff out a little bit. We still need to work on the power supply circuit, because currently I'm still using the clunky Agilent in lieu of a proper power supply for Eurorack stuff. You know, I need to do all the modifications that'll get these analog gauges up and running. We'll work on that a little bit, actually, at the beginning. But for now, I need to block off a location to the side where I can kind of put these things. This is where those cardboard trays came in handy. All the cardboard trays that I have, each one has a project on it, and that allowed me to kind of organize myself and my thoughts. You know, each project had its own little bin to be in. What else do I need to do? Oh, I need to do the end command. We're only doing the end command now. There's no more next command. I just point you at the Discord for that one. Cold. It got cold. We lost like 30 degrees in a day, although it'll be back soon. It's going to be in the 60s the next couple days. Let's see. When's the next John? Next John is going to be the 14th. Time flies, does it not? Does it not? 14. 149. There we go. That's the proper date. There we go. 14th. I gotta start thinking of like Christmas gifts and stuff. Nieces and nephews who have everything in the world. I don't know what to get them. Yeah, let's get these bins. These bins, I had a blowout on the pin bin, so I need to take all this stuff. This is an extra cable. This is for modular stuff, which we might use today. I'll put it over here. Electronic music. This is another DJ Everyday set. This one's at Hex Fest, which is a big festival that those guys throw. It's pretty cool. It's out in a campground in Maryland during the summer. Which, believe it or not, Maryland can be pretty brutal in terms of heat. There was a humid heat and no breeze at all, and so you'd sweat and sweat and sweat, and nothing would dry off. Like your body would not, your sweat wouldn't vaporize and lower your body temperature. And so I now know what it's like to have low electrolytes. You can sweat out all your salt, and you feel like you kind of got the flu, solved by simply drinking a Gatorade. It's pretty amazing, actually. You can clock your various body systems coming back online as you get the salts back in your body. You're like, oh, I can think clearly suddenly. And you're like, oh, I have to pee. Oh, this is happening, and that's how. Oh, my kidneys are back. Like, pretty insane. Probably not great for the body. What else going on? Not much. Not much. We're going to have to do an AutoCAD stream soon. That's easy enough to do. I've got plenty of... Oh, jeez, everything's falling apart. I got plenty of projects that'll take up AutoCAD space, for sure. This analog stuff comes on the heels of a different thing that I'm doing in AutoCAD, but it certainly is in line with all the other stuff. All of the analog stuff we're doing right now is in service to a project that'll involve AutoCAD. So we'll get back to the board design once I have an idea of what the schematic is. Same thing with the module testing module. Basically what we do is we physically build the circuit and test it and make sure it does everything that we want it to do. And then we go into CAD and start putting it together as a design, as a nice organized design. Burp. Burp. This can go away. This goes over here with this. You need to have a good idea of what you're going to do when you build a circuit board. But, you know, those steps, those steps have been uprooted by the availability of cheap circuit boards. It's kind of amazing. Hey, Bothan, how you doing? It's kind of amazing what cheap circuit boards have done for the design process. Because now you can just go into the software and say, hey, I'm sending this to this PCB house. It's like, cool, we'll handle all the files for you. And then you send it, and a week, 2 weeks after you order, you get your full circuit board in the mail. It's like, oh, guess I don't have to use perforated prototyping board anymore. Trying to open up a little space over here where I can pile the junk. I do need to reprint the body for this car, although I want to take this into more of a finely tuned AutoCAD session so we can do a little bit more of the design, so I can have headlights and taillights on it, because I think that would be hilariously cute. All right, there's that. Got that. This is here. Calipers can go, well, I'll probably need them, but I'll put them up here. I'm also starting to work on my desk, project where I'm refurbishing my computer desk, and it'll have rack panels, and so I'll be able to put pieces of equipment in there, like the battery backup, like the file server over here can actually live by my computer where it's going to be a little cleaner. So this thing can move over, you know, this will stay here, and then the rest of this will be dedicated to just stream equipment. Maybe. Maybe. I got to figure that out. It's a lot of stuff. There's a lot of work to do on things. A lot of work. Work, work, work. Work, work. How's everybody doing? It would be amazing if you could print circuit boards at home one day, like a literal inkjet printer printing copper on fiberglass. We're very close to that, actually. And I think in some realms we have that technology. It's just not, it's not like a real printed circuit board. They're getting close, though. There's conductive filaments that you can print with. And you know, Bad Obsession Motorsports, the guys who do Project Binky, they had a whole thing. Their latest video, actually, if you check out Bad Obsession Motorsports and Project Binky, their latest video has them using what is essentially a 3D printer to deposit a solder-like substance onto an FR4 substrate. So they're literally 3D printing a circuit board. It is not advisable, though. I wouldn't go through all the trouble to getting that technology at this stage, because you could just you could spend $100 probably for each board, and you can just get a board house to produce the circuit board for you. And then you put all the mechanical stuff into CAD. You don't have to do all of the, I don't know, just all the trouble that they went through in order to do that. They thought that they needed to be more nimble with their prototyping, but my understanding of the software as it is right now is that that software is amazingly nimble at doing prototyping. And if you pay the money, if you put the money down on it, you can get circuit boards very quickly indeed. So it's not really worth it to have your own PCB printer. It's possible, but not really worth it. They did a really good job of utilizing that technology in a space where I think they could have gone without it. They definitely could have gone without it. Oh boy, I need to do more cleanup than this. This is bad. Things have started to pile up, haven't they? I'm designing a new board we spun up right now. Yeah, because fab houses are crazy. If you pay the money, to get the prioritized, they will not disappoint for sure. Well, I just got here. Be back later, heading to YouTube. I know it's like a little bit against my own personal stake in in the game here to just tell you to go watch a YouTube video. But it is a good one, and they do exactly what you're talking about. And it is possible. It does a decent job. It does an okay job. I'm not going to sing its praise too widely because, yeah, you could just Control-P onto the internet, and your Control-P comes back to you in a little envelope like a week or two later. Their circuit board was going to be very large indeed, so maybe it's better that they did it their way. I don't really think so, though, because I think for the Fab House, if you just eat the costs, $400, you'll also be getting extra boards, because every time they 3D print their board, they get one. They get one board. And, you know, this is the whole process of getting a circuit board made. Part of that process is you get the circuit board to work on the first one. Like, you get that first one in the mail, and then you get all of your ducks in a row, and you get that one circuit board to definitively work. And then you do a revision. So they did several revisions because they made several decisions about stuff that almost rhymed. They did several revisions because of several decisions. No, anyway, so they did several revisions because of the decisions that they were making on the fly. And I guess it makes sense. You know, the circuit boards were printed live and they got it that day. But I don't think the longevity of the boards, I don't know. I fear for the longevity of the boards, and I think that getting a professional circuit board would have solved a lot of their problems as well. No, we decided to do this instead. Well, that's easy. You just import the 3D model, and then all your pads and holes are in the right place, and you have something automated doing all of your vias and drilling. And you can even put in things for expansion. You know, if you feel like, oh, I might want to do something else with this. We've got plenty of space on the PCB. Anyway. Imagine the views you'd get streaming PCB printing. I don't know. Would I get the views? Because all these things that I decide to do that should get me views don't. It's a weird relationship with the projectosphere. That feels a little bit more neat, doesn't it? We're going to be doing stuff with the analog signals today. I did a little bit of reading. I'm probably going to have to pull up a couple data sheets that I was reading and figure out what the heck's going on because we need a couple things out of this, and I have a couple ideas of how we're going to get that stuff out of here. A couple analog circuit ideas. So it's going to be electronics design on the fly. And by on the fly, I mean I'm dumb. I'm very stupid indeed. And I'm going to be dealing with some complicated things. And so in order to get around that, my stupidity that is, my abject stupidity, what we're going to be doing is testing stuff. We'll do stuff physically in the real world, and that'll give us an idea of what happens when, instead of just running numbers. I don't like running numbers. I'm not a numbers guy. I was always very bad at math. Bad at math, good at circuits. We exist. We're real. Some engineers don't do the math stuff as well as they do the creative stuff. I don't know if I'd find my calling in another profession, being a not math guy, but engineering always fit very well. Oh, Rabaz making noises over there. Hold on, I gotta turn his stream off. I'm streaming with somebody else's stream in the background. What's going on here? My other computer. Mute that. Mute the other computer. Oh, we're gonna need this on too. I need to turn on my O-scope. Here it goes. Blisteringly fast power on speeds. So, you guys might not know, but I have kind of a cool neighbor. I have a cool neighbor who's incredibly nice and generous. My neighbor bought a thing, and at some point, I'm going to have to learn how to use it. I got a lot of people who are trying to, I mean, no, it's definitely not trying to, but I feel like in my life at this moment, I have a lot of people who are kind of edging in on my time. You know, time is money, and I only have so much so much attention span and capability and all that stuff. It just feels like a lot of people are suddenly leaning on me. I think maybe it's gotten to be that like I'm of an age where everybody's kids are starting to like become very independent, and they suddenly have all this free time, and they're kind of leaning on me for it. But my cool neighbor, not necessarily trying to take up my time, unlike other avenues, but so my cool neighbor said, "Hey, I got one of these things, these Flipper Zeros. Have you ever heard of it?" And I'm like, "Have I heard of it? I tried to buy one, but my credit card said, hey, this is too shady. You can't buy this." He's like, "Well, I have one and it's collecting dust. You want to check it out?" And I'm like, "The hell I do. Like, yeah, absolutely I want to check it out." I have absolutely no idea what one does with a Flipper Zero, but I will endeavor to try to get arrested as hard as I can with it. Apparently you can do some pretty crazy stuff, and I think aren't they like illegal in India or something? In Indonesia? I don't know. Somebody made them illegal. Some country outlawed these things. I wanted to get one for some time. I just haven't bothered to get the credit card to not reject the Flipper Zero website. But he's given me one, and I can play around with this one to whatever end. I don't know if it's permanent borrowing or if it's temporary borrowing until he can get around to using it. It sounded a lot like it was one of those things where we just won't really talk about it. I'll tell him what I've been able to do with it at some point, and it'll be a conversation starter, and he probably will never ask for it back, which is pretty crazy. So I don't know what I'm going to do with this thing. I don't know what I can do with this thing. Apparently you can do a lot of crazy stuff. We'll have to try to find something cool. And he also has the Wi-Fi development board, which I assume is just, yeah, it's just a thing you plug into the top, and it looks weird. Interesting product, this, the Flipper Zero. Recently got a card pewter. That sounds kind of cool. It sounds a little bit sci-fi. Yeah, apparently you just bought a Bing. There you go. Now I have the capability of breaking into Wi-Fi, which I'll have to look at some point. Bonk. I would like to convert this house to Ubiquiti enterprise level stuff, because it would be nice to have reliable wireless. It's not that reliable. I'm using a lot of consumer grade stuff, and it's not great. From N5 Stack, I vaguely know the name, but I don't know nothing about it. I vaguely know M5 Stack. I've heard of that before, but that's about as deep as it goes. So yeah, I really want to figure out what I'm going to be able to do with this thing. I've got to start looking it up. I never seriously wanted to get a Flipper Zero. This is, oh, hey, Flatulent going on, what's up? So I have a cool neighbor, I was saying. I have a really cool neighbor who went, hey, you ever heard of the Flipper Zero? And I'm like, have I? I tried to buy one. And they rejected my credit card because it was shady. Credit card said, hey, this is a shady website. You're not allowed to buy this. And I'm like, wait a minute. M5 Stack sounds like a BMW pileup. I think I've been responsible for a few M5 Stacks in my day. I've heard of it somewhere. I don't know why. But anyway, so my neighbor is just like, hey, I got one and it's collecting dust. You wanna play around with it? I'm like, do I ever? So apparently this thing is like a hacking, like, I don't know, the nadir of all hacking wireless signals. So maybe we can listen in for my insulin pump or something on this. I'll have to figure it out. It's, again, this thing dropped on my doorstep is a lot of research that I didn't expect to do, because I sat around here and I said, what wireless signals do I have running around the shop that would be really interesting to hack into? Wi-Fi? No. Bluetooth. That's my insulin pump and like keyboards and stuff. Nah. Airplanes? I mean, I've tried that before with the Raspberry Pi and it didn't really work. The RF situation around here is kind of bleak. Cell phone signals do not really get through. It's all Wi-Fi. I don't know. I don't know what I'd do with this thing. There's no security systems nearby that I would be able to mess with. It is, yeah, that's one thing, is that people use it as the ultimate remote control. So I could hack into the garage, my own garage, my neighbor's garage. What am I doing with my neighbor's garage? I don't give a shit about their car. I don't need your car. They all have those Porsche SUVs around here. Everyone, and they're all white. I don't know what, it's very weird. It's very weird. Everybody bought the same car. I don't know if they coordinated or if one person bought it and then recommended it to everybody else. But in the end, there's a neighborhood that's full of those freaking things. It's very strange. So yeah, I don't know what I'm gonna do with that, with the Flipper Zero, but at some point I'll look into it. I bet you can make all the garage doors in the street do the dance. That would be... It's that commercial with the light switch that doesn't do anything. I don't, you know, can I pluck a drone out of the sky? That'd be kind of neat. I don't think that'll be able to do that, though. I don't think that'll be able to do that. I once got contacted. They wanted an RF engineer for one of those companies that was making a device that would pluck drones out of the sky. I thought that was kind of cool. It's like my reverse engineering and my signal background kind of put me in a unique position to work for a place like that. But I think they wanted to pay you like peanuts because it's, you know, let's hire a millennial. I have a couple gum wrappers that we can give them for a full-time career. So it was one of those things where I'm like, I don't want to be exploited. And then these devices, these handheld drone defeating devices start appearing all over the place. Which is funny because in order to do that, they need a lot of antennas that can operate over great distances, pretty much as far as you can get it, which puts you in the territory of having a Yagi antenna, which is a bunch of poles sticking off of another pole, and because of physics, you can't make it very small. So all of these like space guns have these huge radomes on the front of them that make them look ridiculous because antennas are ridiculous. They shouldn't exist. They work in an area of physics that is so weird that other engineers say, that's black magic, I'm not touching that. I know little about RF. I know a little about RF. I know enough to be dangerous and how to copy other people's work. What I don't do is E&M field equations and stuff like that. I am not good with that stuff. Again, not good at math. Good at coming up with ideas, not good at math. So, are you a ham? No, I looked at the test for the ham and I was like, I can't really commit most of this to memory. I was like, at this stage of my life, I just don't want to, I don't want to do that. Fat just recently, go ask the RF devil. Yeah, it's the horrible Liac magic of RF. Why is the most burnt, disgusting area of my desk the one where the microscope is? Jeez. Probably because we work in that area a lot. Get this stuff. Let's get this stuff on camera here. Yeah, so we're going to be looking at this chip right here. This guy. This is the V2164M. It is basically 4 voltage-controlled amplifiers in one little package. But the caveat on the V2164 is that instead of making voltages on the output, it makes current on the output. So we need to figure out how to utilize that current. It's usually through another op amp. And then we've got to do a couple things to that in order to make it mix properly. But yeah, that's the stuff we'll be dealing with. We'll just be throwing circuits down and seeing what kind of stuff we see on the other end. It'll be fun. We can actually have a little bit of fun with the sort of the circuit planning and design kind of stuff. It'll be neat. The problem with my tiny hand gag is that the tiny hands are not warm. And so like 10% of my screen is the execution of the tiny hand gag. It's better if it's like this, where you don't see my fingers shoved up the plastic. But on the thermal cam and on the hand cam, it completely gives away the gag. So I'll have to figure something that I can do with these hands. Maybe I can make an ultimate slapping device. Put them on the front of Nerf darts and have them shot at me. Working through some current voltage regulation stuff with my board. Something seems wrong with the ASIC. Oh, ASICs. That sounds fun. Yeah, I didn't have much of an idea when we tried to fire our ideas at this thing before. I've read some data sheets now, and I've got a couple little circuit ideas that I want to execute. And hopefully on the outset of it, we have a good thing. Could BTS have a hand for pointing at names? Burp. Maybe. Yeah, I got to think of some stuff. Burn the Subs needs my attention again, and unfortunately, I've had people trying to sway my attention back and forth on various other things. It's just one of those things about being an electrical engineer. Is people go, I have this idea, and you then recoil in horror because you know that what they want you to do is dedicate your whole life to getting their idea done for them, and their idea is primarily electrical, and it's like, I know precisely how much of my time that's going to take up, and I don't want to say no to you, but it's one of those things. I'm already embroiled in my own project, you see. Not our A6, but we use it. It has a little programmable core. It's not working as expected. Oh, man. Is that the chip you were live bugging last week? Yeah, it turns out. So it turns out Oh, that's burn the subs. Wait a minute. It turns out that these little breakout boards are cheap now. They used to be very expensive, actually. These things used to be expensive. But now these are ubiquitous and they're cheap and you can find them very easily. And I can get them delivered second day. So I now have a bunch of these boards where we can break out surface mount only chips, because I sourced surface mount. I could have gotten a through-hole version of this chip, but I neglected the fact that we would be breadboarding with it. So we can just throw it up on an adapter and we're good to go. I could also do surface mount op amps, but that seems a little wasteful. Plus, this takes up so little room. So, house music. This is a DJ Everyday again. I have to find music. I don't know how I'm going to be able to do that among all of the other things that I have to do, including walk the dog, feed myself, try to sleep, look for music, masturbate. You know, all the things that you normally do. I'm having the leads send me another board and also requested 5 more samples of the chip for the manufacturer. Damn. I mean, like, what kind of debugging do you have on something like that? I've never used an ASIC that had, like, programmable space in it. But I would hope that they give you every opportunity to use their device properly. It's kind of crazy. I mean, we have somebody in, Nothing's Working in the Discord, is working on making a custom digital gauge for his car, which is a great project. It's a really cool project. It gets you exposed to a lot of cool things, but he's having trouble with analog level sensing in the ESP8266. So, like, really cool project. You could reprogram that on the fly with the Arduino IDE. You can install it in the car, and you can have everything up in there and running and working. But, you know, you want to know that what you're getting from your sensor is the proper stuff, and they're having some trouble with the signal levels and stuff. But, like, that's different from having, like, an ASIC that has built-in features and a little program space. Because with the Arduino, you can tell it all kinds of debugging stuff. You know, that's inherent to the Arduino. There's some logic debugging, but like enabling stuff in an unrelated register creates an odd effect. Oh God! So it's made like a low-level microcontroller. I hate those. It's so bad because your references have to be referenced to a reference. You need 6 documents open in order to know what you're supposed to specifically be talking to. I hope I'm getting close now. Yeah, I mean, it's the fun part, right? Is you get to figure out. At least with your application, you don't have just one. You can test 2 different microcontrollers and say, oh, okay, so something here is broken. But with like a special ASIC with program space, I guess what you're doing is you're getting another one and you're going to test them. It has a custom language. Oh no, no! That was like when I got FreePie for my joystick, is I had to learn their specific type of Python in order to run multiple joystick devices together. It was a hassle. I had a friend over here yesterday because we went out to get lunch, and I have most of his joystick stuff sitting on my wall. My wall over here, the forbidden wall of devices. I got the IBM Model M keyboard, Sci-Tech X65 FS or whatever. It's the force-sensitive joystick that you wouldn't think, but it's terrible. It's very nice to do like accurate movements with. The joystick doesn't move though. It doesn't have an X and a Y axis. It reads the microscopic bending of a pole. There's a pole and it reads the microscopic bending, whether it's twisting or X or Y, right? And so when you're piloting something with that, you go, oh no, I have to get out of the way. And so you go as hard as you can because you don't know where the guardrails are. There are no guardrails. So you eventually punch your desk as hard as you can. When the base slips out from under it, you go bam, and you hurt your knuckles in the process. So I attached that to the desk with a big clamp. It's an extra piece of metal that I had my friend drill out. This is before I had the drill mill set up. So a friend of mine got this like engineered, and he built this little base, and I attached it to some 80/20 rail, and I clamped it to the desk. And it turns out your arm gets very tired when using that thing. So that is unfortunately going to sit there. That's where it lives now. We have joysticks that my brother bought for a different project that we put into use as like its own little custom joystick. I've got my Thrustmaster T5 billion M. This is the Sci-Tech throttle, and I plan on using this. I plan on using this throttle because this is an awesome throttle. It's splittable. You can split the throttle. It's got a big wheel on it. It's got a little like mouse on it and everything. So if we can like reverse engineer this and get it to use in my dual joystick project, that would be great. I have a miniature chainsaw just in case. VR is, of course, collecting dust. This is from my friend's Thrustmaster that's taken apart and sitting over there. I got to get those two back together. We got to rebuild that. And there's my Pentium 2. Because it's all about the Pentium. Oh, and then the gate shifter from the BMW. The E46 M3 Steptronic shifter with the little forward and backwards bump. Works perfectly well. I'm just not used to it. And a project that I don't know when we're ever going to get to these, but these are the Star Trek emotes. Or sorry, Star Trek ornaments. There we go. Christmas tree ornaments. The Star Trek Christmas tree ornaments. I have a whole collection of them, and they almost burnt down my house. They almost burnt down my freaking house. They, the bulbs, the older ones have bulbs in them. And something happened with the voltage that went to the bulbs, and the bulbs got really, really hot. And so a lot of them broke or melted. And I kind of need to go into those, but they're all glued together. I don't know how they go together. They're all glued together in some way, shape, or form. But yeah, the bulbs almost burnt the plastic and burnt my house down. Fun times. Wait, what is that cable? Is that a giant USB cable? Yeah, I guess it's a giant USB cable that's just there for some reason. Why did that get there? Come on back over here, everybody. We're going to poke at some of these analog circuits today, so that's why we're concentrating on just this stuff around here. Okay, let's see. What else? What else is going on? My friend and I were talking joystick, and I kind of really want to bring back the Sci-Tech joysticks, because like the dual joystick setup has all its hardware sorted out. I don't know if we did any reverse engineering of the Melexis MLX 9033. It's a chip that has a magnetometer in the top that'll read a magnet going over it in a hemisphere. So it's able to detect, the location of the joystick. It's a cool little chip. And if we reverse engineer that properly, we could hook it up to our own Arduino, and then we can sense both of the joysticks, all the buttons, and then I can have that throttle and all the other stuff. I'm doing it in a decidedly not flatulent gonad-esque way. Gonad appreciates having all the analog signals, and I hate them. So I take all the analog signals immediately into digital, and then I have all the digital signals coming into the microcontroller. Because I do not like dealing with them. I would scale them on their own and do all that stuff in software. I'm much better at doing that. That said, we are about to wallow in analog signals. We're about to do nothing but analog signals. With all these chips I bought. I don't know if we should use the dual transconductance amplifier as our final stage of amplification for this device. That might be something that I want to do. In which case, that takes it very close to the M303's final stages that I've yet to reverse engineer. I have not reverse engineered those. Got a lot of projects on the mind. I got a lot of projects in the shop. That somewhere. Put that somewhere weird. Right there. So it looks like something's disappointed at me. You just want to talk. Actually, the fingers bending is a little bit weird. As we proceed. What else do I got going on? Not a lot. Hey, Tinkering EE, how you doing? Let me make sure I'm up on alerts. Oh, when I have to pop out, sorry, YouTube chat, I forgot about you guys. I knew I was forgetting something. Sorry. Oh yeah, that means I need to open it up here. And then go to YouTube. Oh, did I get a shout out? I'll close that. And then, yeah, that's not the right one there. Here, You can see behind the scenes here as I get all of my stuff sorted out. YouTube, no bother VOD. There's a wire right on top of the keyboard. I hate that. Go here, make sure it's muted. It's muted. Wait for chat to pop up. Pop out the chat. I don't think anybody has talked. I don't see nothing. There we go. Now these guys will be up on screen. You guys will be up on screen. And then I go to my alerts. And I 35 viewers 2 days ago. Hey, thanks, Gonad. And then that Louis raid, the Lunatic Live raid, is very awesome. This was not. Gigantifying emotes is not cool. I have it enabled, but what was that? Get out of here. We got to work a little bit in Node-RED and in the near future. Maybe I just need to do this because this involves turning a robot on in the chat in order to get alerts for stuff like the Twitch API. I need to get a functioning Node-RED Twitch API, and so that means enabling the robot and giving it the keys and the ability for it to get more, like to reissue all of its keys and stuff. It shouldn't be too hard to do. I just need to find a plugin that has enough functionality, because that's going to become the front end for all the interactivity in the shop. We can get the fart box back. We can refurbish the fart box fairly quickly, and I'll just have to have it either act like a Tasmota device, or it can maybe be its own thing, and just Node-RED will ping it and get it to go. And maybe I could even make it do specific. I could do 1 through 9. I'll make Node-RED do the randomness of the 1 through 9, and then because there's 9 farts on it. It's a dollar store fart box. 9 fart noises that you can hit a button to enable. They all have different lengths. So my software in the fart box knows how to get on the Wi-Fi, and it knows the lengths of each fart to play back. And then it hits the button, and then waits a certain amount of time, and then goes back to its next instruction. So we can make that work transparently, or we could make it have its own random. I think moving random over to Node-RED might be good, because then I can even use the like international, whatever that website is that has the random thing. It's like it uses radio stuff in order to make like a true random number. I could do that. I could point it towards that with Node-RED, and then we'd have truly random farts. I don't think it really matters that much. I think for our intents and purposes, our not quite truly random microcontroller randomness is fine. But anyway, I can have Node-RED make the decision on what fart to do, and that way we could have special things that take over that functionality. We can have things that go, oh, no, we're not quite doing that. We're gonna do this specific fart. It would be kind of funny. Button 1 through 9. But yeah, that Node-REDing means that I would need to reprogram the microcontroller a little bit. Not a lot, but figure out how indeed I'm going to be receiving messages, in which case maybe I just turn it into, I don't know if Tasmota versus Arduino, I don't think there's like a plugin that I can run. Which means it probably needs to do like HTML stuff, right? I need to parse an HTML thing that would be sent to it. I don't know how that stuff works. I'm not quite a network engineer. I don't know how intranet things function. Again, I can learn. Engineers always, haha, I need to learn somebody else's entire job now. Again. That's what we do. Jack of all trades. Jag off and done. Dude, what now? What did you do? Disgusting. Keep that to yourself. Can't. The wires are the wires. They're just going to be there today. All of these wires. I have an interview tomorrow. We'll see if the team likes what I already know and if they want to invest time into teaching me the new thing. I went through all that when I did the security clearance stuff. It's kind of amazing that you're brought in, and then for the duration of your investigation into whether or not you're blackmailable, they investigate you, and you basically just walk into a room and sit there for your job. They basically give you some documentation and goes, study this, it's what you'll be doing. And you're like, this is like old. There's dust all over it. It's like, okay, this is what I'm doing today. I made a lot of progress on some projects that I was doing at the time, though. I was able to do like circuit design and stuff like that while going into the office to just kind of sit there until they were done investigating me. But that's kind of what it feels like. It's like it feels like coming into a new job with no knowledge of the job you're doing, and then they have to train you on it. It's like, wow, when do I become useful? Apparently, they billed a lot for me, though. They made a lot of money. Make Furby flart, Furby art, Furby fart, Farby, fart be with us. Yeah, I do want to do something with the Furby, and I don't know to what end. I don't know like how the Furby functions inside, and because people have done all kinds of stuff with the Furby already. I bought that a couple years ago with the intent of doing something with it, and we just haven't had the overhead project space. Everything's been taken up by Burn the Subs, and my subsequently burning out on Burn the Subs. I want to get Burn the Subs into some kind of a form before we look into the Furby, because I do want to make that Furby like do a little dance when fart noises happen, because it'll be funny. So like 90% of the projects around here are basically formed around the comedy of having something weird. So I said earlier, revolving door around here, right? People come, people go. For those that didn't hear, I have a very cool neighbor, and my very cool neighbor bought a Flipper Zero, something that I was unable to do, because I figured that voice in the back of my head said, you don't really need a Flipper Zero. You don't really need a Flipper Zero. But that neighbor bought one, and his credit card was not immediately declined, so the voice in the back of his head didn't stop him from buying it. I was going to have one of my own, but the voice in my head said, what are you going to do with that? Said, yeah, you're right. But the neighbor said, this is collecting dust. So now I have a Flipper Zero and a Wi-Fi kit for it. So, okay, what does one do with a Flipper Zero? I started looking at them yesterday. Apparently, they're pretty much a Swiss Army knife for wireless signals. Only word I like to hear when a Furby is mentioned is thermite. My Furby is sick of your shit. Look at that. It's sick of your shit. Yeah, so the neighbor actually grabbed the Flipper Zero, and he immediately... Oh, there's a digital pot lathe on this thing, too. Neat. He immediately gave it to me. Like, here, maybe you can do something with it. And I'm like, okay. Like, far be it for me to say no to something that is considering being illegal, considered to be no, what do you call that? I don't know. One country outlawed them, and I know airport security really, really hates these things. But now I have one, and it's pretty much, I don't know, Swiss Army knife of RF hacking capability. I have not even looked into what these things can do and what I can do with it. I don't know. I could probably inject a bunch of insulin if I really... it's got apps, it's got settings, I don't know. I got to take a look at what this thing does. Ethical hacking. A couple more quote signs on that, Gamer Pino. Turn off. Turn off. I turn you off. I am happy, my friend. No, you're about to turn off. There we go. Off. There it is. Gotta hold that for a long time. Yeah, so that's something that I can look into is what I am doing with Flipper Zero. They are the Swiss Army knife. I'll have to figure it out. I mean, I got the Wi-Fi thing too for it, although I don't really want to hack into my own Wi-Fi, to be fair. Like, what use do I have? Why do they put a sticker over the picture of it? I wonder. Strange. Put this to the side. I mean, like, my pancreas is pretty much functioning because of wireless signals. I've got the cell phone speaking Bluetooth to both a glucose sensor and an insulin pump. And those packet structures are known. They're known packet structures because they're in the Bluetooth low energy documentation, whatever it is. We've looked at that before because we were looking at Bluetooth low energy steering wheel controller from Granite Devices. We fully reverse engineered it to the degree where we didn't really reverse engineer it, but we made our microcontroller fake being a wireless modem that's connecting to a Bluetooth low energy device. Very eclectic thing to do, very hackery thing to do, very sort of reverse engineer hacker thing to do, is to fake being another device in order to get the functionality that I need out of this thing. Out of the steering wheel was the example. But like my insulin pump and insulin glucose level sensing is all Bluetooth. Why would I hack into it? Why would I hack into it? Why would I do that? Why would I do that? Why? What, to what end? Why would I want to do that? Why? I don't want to do that. It's keeps me alive. Like, what else can I do? Hack into my own Wi-Fi? That doesn't sound fun. There's been some people that spam the glucose monitors, and it's not good. Yeah, why would you want to do that? Why would you do that? To make the sounds go away. That, unfortunately, is not a thing. The sounds are baked into it. Hack my car key fob. I mean, it's my car is of a generation that uses key lock, Keeloq. So I could do that, and I could actually put my remote code into the number space where it would take me several years of pressing the button for it to catch up and end up unlocking the car. I could lock myself out of my key fob forever. That sounds like great fun. What fun that is. What fun we're having. Some cars you can get into the cell phone on, like the communications protocol. They've been able to roll down the windows of a Subaru by listening to the person unlock their car. Looks like I finally have the right voltage on the ESP. Now I need to hack up more code. Hell yeah, finally. That's great. That's good progress. I'm sure it was very frustrating dealing with weird voltage levels. Like, as soon as you start this project, you're like, I'm gonna do something that's a little bit out of my comfort zone. I'm gonna involve a microcontroller, and I'm gonna code it. And then you code something for the microcontroller, and something analog happens, and it's completely out of your wheelhouse, and you're like, I don't have the tools or the knowledge to troubleshoot what the heck is going on here. That's when these projects typically run into the big speed bump that causes them to collect dust. And Nothing's Working has luckily had a breakthrough in comparing microcontroller to microcontroller and getting the proper voltages on everybody. That's very, very good. I had a car I could break into with a wooden spoon. Yeah, those are great. There's a caveat to all the key fob. I'll ask friends. I can't remember what happened with them. I'm not going to just immediately play around with the key fob. I do know how key lock works. And key lock, there's a way you can lock yourself out of your car for years. You can also undo that pretty easily too. There's basically a round of values that get thrown into the encryption. And if you're outside of that round of values, it'll either update the round or it will reject the code. And so there's this big rejection space. There's a tiny little sliver of that wheel that is codes that are accepted or codes that configure where your round is. And so you'd be able to continue that little space of numbers until you get back to where your key fob is. Didn't expect this was a struggle, to be honest, since I did almost the same on the Arduino Nano, but that measured the voltage fine, unlike the ESP. Yeah, that's a weird thing, huh? I have broken into a car with a coat hanger. What else have I used? A lot of coat hangers. I had to get my wallet out of a car once by plucking the thing with a coat hanger. I've done. No, that was using a rod. So yeah, mostly universally, the way that I've been able to get into cars is by pushing the unlock button from the window. Back in the day, you could use a Slim Jim to get in, but that doesn't work anymore on the models of cars that I've been trying to break into. But it would be kind of interesting doing it via a little device, just scan the over-the-air code. And I remember finding stuff when I was first learning about a key lock. I remember finding, researchers were able to decode the universal secret numerical code of key lock that was in basically all cars that used that system had this secret code. And then there was also a manufacturer code. And so they were able to get the secret code and the manufacturer code by hooking a resistor up to the power supply of the device and figuring out what the microcontroller was doing, what numbers it was shuffling around, and then they were able to get identities on those numbers in how it's reading the memory and how it's doing the math processor and stuff like that, just by the amount of current that the microcontroller was utilizing at the time on a very fine time scale. And then they took that into whatever computers they were using to decode it. They got the code, and then all the manufacturer codes started getting leaked because they had the other universal code, and so you started to be able to get all of these different manufacturing codes. And at the time I learned everything, it was so broken down that you could Google and find these devices that were little touchscreen devices that had all the manufacturer logos on it. You'd select BMW, and it would start listening over the air. And somebody would go to unlock their car, and it would grab that signal over the air and say, this is what round they're on, this is the code, this is the secret code, and here's the one, whatever was transmitted. And then you could get it so that they were unable to operate their own car. Craziness. Now, that didn't have anything to do with the vehicle lockout systems, though, or starting the car. But now cars are way more computery, so it's a matter of man-in-the-middle cell phone station hacking in order to figure out how to get in. I had another car I broke into with a string and a twig. That's pretty crazy. It was something about being able to only do something once. It may have to do, that's pretty much all I can think of it would have to do with, is that secret code round, putting it into a space where it'll not match up. It won't advance the code round, and it'll think that your clicker is supposed to be on a much greater number, and you can sit there clicking your remote for years, and it won't get up to the number where it accepts the code. It has to do with how keylock works. You got to look up keylock. Keeloq. All right, I've been doing this for a little bit. I've been chewing the fat. We should probably get to work, which means I need to pull up a couple data sheets. One of the things that I would like to do, well, okay, let's get started then. Let me where's my music? Where's my music? There it is. Bass. Yeah, you do that. Yes. Hi, how's it going, everybody? Welcome. We're doing analog stuff today. I didn't do a Blue Sky chart. I don't know what they're called, tweets. I didn't do the Blue Sky update. I probably should have. My account is very quiet, and I maybe that's a bad thing. I should be trying to foster more engagement. It's tough to do. But anyway, so we're looking at analog signals, and we're looking at making a mixer. Julian, my good friend, for many, many years, he's wanted me to build him a synthesizer, and he seems to be getting me to do that by trickling little tiny tastes of projects at me. This time he wants a 2-rack panel wide mixer, and the mixer is to take 2 left and right signals and mix them together onto a stereo plug. So basically, a headphones out. And I want to use a particular headphone out chip for this because it makes my designing job a whole lot easier. It doesn't need that. I could make it just use like an op amp going into something, but like I want that special flair. I want it to be like this is designed for high quality headphones. What's up, Matt of you? So I want to use this chip. I haven't ordered it yet. I haven't ordered the chip yet. We need to make a particular signal that goes into this chip. That's the whole thing that we're trying to do. And we need to fit on multiple amplifiers that are adjustable into what is a very small board. We only have 10 centimeters by 100 centimeters. 10 by 100 centimeters, I want to do this in one board. I want to do them one PCB, and I want all the chips to fit on that PCB. It's not looking good. We were able to get all the controls to fit, because that's 4 input plugs, 3 potentiometers, and then 1 output plug. All of that has to fit in 10 by 100 millimeters, and it does. Barely. It barely fits, but it fits, which is unfortunate because that means that we now move on to the electronics design of the whole thing, and I need to figure out how much technology precisely we can fit onto one side of this board, a 10 by 100 millimeter. It's not looking good, but we need to figure out what our schematic is going to be within the purview of making a high quality low noise headphone amplifier that can be adjusted and is stereo. And so that brings me to the V2164. The V2164 is, by all intents and purposes, it is a quad voltage controlled amplifier. We have 4 of these little voltage controlled amplifiers on this chip. The chip works by converting current. Well, current in, current out. So we're actually going across this 30 kilo ohm resistor here and the 500 ohm and basically converting the voltage into current, and then the current is whatevered by the amplifier based on the voltage input, and then its output as current. So a mixer can be as simple as this setup right here. And then you have voltages that control the mix of your 4 channels into one op amp. And the op amp is in what's called transconductance, a transconductance configuration, which I guess means to say that it inverts, but it also converts conductance into voltage on the output. So this is just frequency filtering now. This has nothing to do with the gain of the op amp. Now we can get by doing that. We can do 4 channels. We have all 4 of the inputs plugged into this. We mix the 2s, and then we take them out with another op amp, but I still need control over the 2-channel mix into the headphone amplifier. So we need another V2164. I'm using only 2 of the channels of that for the right and left output, which means we've got 2 of these current thingies floating around looking for a job. If we can get to use those, that would be nice. I'm not exactly sure how we would be able to do that, but oh man, there's just a lot for me to deal with, a lot for me to consider on this circuit. In addition to the filtering that we're doing, or the mixing that we're doing, I need a differential signal coming out of this thing when all is said and done. So the question is, well, can I connect this in a non-inverting form? I think I saw a circuit where somebody put a resistor to ground, and then that would convert, V is equal to IR. So you measure the resistance across, or measure the voltage at the resistor, and that's dependent on current. So you turn it back into voltage that way. So you can put an extra resistor in there and have a non-inverting op amp setup. If I take this current on this line here and I convert it to voltage with a resistor, and I directly output that without the op amp here, what does that mean in terms of delay of signal? Because what the headphone amp wants is a differential signal. Let's open up the headphone amp circuit. So we'll play around with some of these circuits and figure out what's what direction everything's going in. It'll mean putting stuff up on the scope and seeing where the pieces lie. This is one circuit that I got for differential, but I realize that it's wrong. I can't use this because this is a specific product. This is a specific op amp that I don't have that produces a differential, and it can if you give it a signal input for a differential, but it's got 2 outputs. I don't have that. So I think we're going to have to play with buffering and stuff. Yeah, shunt resistor measuring current. Well, I don't know what our shunt resistor will be in the circuit. But yeah, where's the let's see. Oh, this is the SS2164 and the what is it? The one we had. Where's the one we had? V2164. They are different. They're both 2164. They're both transconductance amplifiers. One of them has slightly different properties than the other, which can get confusing, but there are more examples in this data sheet for the type of stuff that we want to do. So like here we've got a 20K, whereas we'd use a 30K on the other one. But then we've got, the TLO72 doing pretty much the same stuff. Hey, Lawn Dog. Yeah, and I don't know if I want a shunt resistor in there. I don't think that's quite what I want to do. I looked up some circuits, and some people were using, I forget what the value of the resistor was on the output. A lot of talk about impedances that I just didn't get. Linear control circuit. So like we could implement something like this linear control circuit into our design. It would require another op amp, which is getting kind of ridiculous. We got to be careful about the number of op amps that we allow into this circuit. Temperature compensated exponential voltage to current converter. Oh my God. temperature compensated. And this requires how many of these things? 3? Oh my God. That's a little bit much. Do I want to temperature compensate it? Maybe. Oof. But yeah, this data sheet, the SS2164 has way more. Oh, economical low frequency oscillator. It has more examples of what you would do with this thing. The converting over to current control is a weird thing, and I don't know why they do that. I don't know why they want to do that. I guess it makes more sense for like controlling filters. It would be great at controlling filters, making a voltage controlled filter, but we're not a voltage controlled filter. Here's a little diatribe. This is just a little thing on transconductance. So transimpedance amplifier circuits. It'll give you an idea of what the equations look like, and I immediately burst into ash on seeing equations. Equations in my electronic circuits? No, thank you. And then where do we have? Let's see. Where's that link? Something, something, something. Where did I post the headphone amplifier? Huh. Oh, it's way up here. Oh, yeah, it's in this big block. I had a big block of links that I put in. This is the one that I want to use. So, you know, last time we were talking about the headphone amplifier, I hadn't really selected one. I did a little bit of looking into it, and this appears to be the one that I think will do our job the best. And it'll take a bunch of design stuff away from me, so I don't have to worry about it. And it comes in a quad flat no lead, so it'll be small. So in applications requiring a high power output, now Julian mentioned that, you know, he may want to drive equipment with it, or he may just want to plug headphones into it. So I want like the big DJ headphones to work with it. I don't need audiophile level, like high voltage headphone amplifier. You know, he's not going to plug a set of membrane headphones into this thing. He's just going to use normal studio headphones. So they're kind of like a little bit heavier driving those. So I'm just going to get a chip that just says, hey, give me some voltage. I'll do whatever you need me to do with those nice headphones. So replace costly discrete design, allows music, not the amplifier, to be heard. TVA's current feedback AB amplifier architecture delivers a high bandwidth, extremely low noise, and up to 128 dB of dynamic range. One of the advantages of this thing is going to be the filtration that it does. I think it has a little bit of pop filtering and stuff, and it doesn't do bass boost, and it's not digital. Those are the requirements. I can't use digital stuff because we don't have room for a microcontroller. I mean, we technically do have room for a microcontroller, but I think that would make what is otherwise a mostly analog design into this digital nightmare. Digital nightmares beyond our ability to fathom. I mean, if I did do it digitally, I could put like an AT-Tiny 12 on there, and then I would have the analog voltage levels of the knobs going into the micro, and then the micro would control whatever other circuitry is on the outsend of all that stuff. And it could allow me to do digital normalizing, which I don't really think is a requirement, but it's something Julian mentioned about normalizing the inputs. I think maybe normalizing the inputs is just going to be a potentiometer that's on the back of the board. I think that's the best way to do this, although I have no idea what the design is going to look like at the moment. We're going to get there eventually, but let's, so we're going to use a circuit similar to this. So what's happening here? I feel like we have transconductance amplification happening here. I think that's what's going on with these OPAs. And then we have differential outputs from whatever DAC. So we need to, in order to power this headphone amplifier and use it properly, we need to get some kind of a differential signal into its inputs. Look for a version of the audio IC that could be put in a socket. This is a 10 millimeter by 100 millimeter board. Let's open it up in CAD so that I can show you precisely why that doesn't work in this project. And just close this. I have it open in another computer. I don't know if my new license agreement means that I can open stuff in multiple computers. I referenced Scanlime the other day. I had to research something, and I brought up Scanlime, who is a friend of the show. Hold on, I'm looking up. Oh, Fussroda, Fuss. I don't know what Scanlime is up to these days. She was making a flying system for the camera in her shop, and that was years ago. That was like the beginning of the pandemic. So I don't know what she's up to these days, but she's another kindred spirit, another maker on our level, and probably some really interesting stuff going on. It's just my research of a particular topic took me to her streams, and I remember around the time. No, they weren't around then. It was pretty much the beginning of the pandemic. People were like, "Have you seen this person?" And I'm like, "I don't know who they are." I looked them up and like, "Oh yeah," and they were like the only person to have a resource on this particular project. We're loading. But yeah, I was like, Scanline, I wonder what she's up to. She's still doing cool stuff. There we go. Okay, so let's open up the Julian's Absurd volume knob. Now this thing is for volume, it's for control signals, it's whatever, you know? I don't know to what useful end you would get control signals out of the other end, but simplify modeling with configurations. Create and manage multiple design variations from a single unified model. That's an interesting idea. It'd be nice if I could do that. That's actually a very interesting idea. So we did a 3D render of a PCB. It's a little different now because I've been kind of throwing parts down onto the pads, but we fully minimized the Donkey Kong connector to its absolute bare minimum, which means that there won't be copper on the little circle area at the bottom of this thing, but it's not making another hole in the board. It doesn't have to do that. It just needs a little bit of room at the bottom of the connector because they kind of min-max the space that they have for a mono 3.5 millimeter plug going into it. But our stuff is just not that big. It's not that big. You see the width here of this chip is the same width as this chip here. That's my hand. Stop looking at my hand, weirdos. It's the same width as this chip. So we have about this much space, a little tiny bit more. A socket is not gonna fit. It ain't gonna do it. Just ain't. It just ain't. Unless I do some really weird stuff. But now sockets are out. Not sockets. That right there is, well, I guess it is 7.9 millimeter. That could fit. We need about this much area to do the pads, which gets us to 10 millimeters. So anyway, I'm not doing through hole in this design. There's no way in hell. And the ability to change out parts is completely beyond. We just don't need it. So anyway, I want to use a particular headphone amplifier, and that's because this is a pretty simple circuit. We will have a quad flat no lead part. Signals that are mixed will go into the left and the right channel. It might be a little complicated for me to actually feed this thing differentials. I can put this into a single-ended mode. We would want to test that when I get the chip. I'm gonna have to order just this chip from DigiKey, and it always feels kind of bad ordering a singular part from DigiKey. I'm ordering just one little cut tape of these little audio amplifier chips. But this is a current product at DigiKey, so the TPA 6102. It might be a little bit old, but it seems to still be in the pantheon of current parts. Not to mention the fact that this is a little bit of an eclectic application. I don't think I'm going to be selling 10,000 of these things. But this little guy right here, $3 a chip on the cut tape. Class AB, headphone, 2-channel, 80 milliwatt. Differential input, short circuit, thermal protection, blah, 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 blah. 14-pin VQFN, exposed pad. But yeah, we'll be able to get one of these into a breakout for it. And it might be, we might dead bug it because it's a QFN. QFNs are easier to dead bug. You flip this chip over and solder wires to everything. I would love to live bug it, but I don't think I have the setup to do that. I don't think, unless I put tape over the ground pad, then I could put it into one of those big weirdo breakouts. But anywho, we'll get that down onto a pad and we'll get that down onto our test setup so that we can actually get the thing fully expressed. This is a mixer. This is not something too complicated. So my guess is that our circuit is going to look very similar to this little guy right, where is that thing? Very similar to just the example of a mixer circuit. Order 2 of them? No, you order like 10. I'm going to be spending $30 for 10 of these things. Yeah. You always get extras because something like suddenly will go wrong soldering it. Like I could hit it with static electricity. I could hit it with too much heat. I could drop it on the floor and it could disappear. Anything can happen. You definitely always want to get extras. I'm not ordering one singular part from DigiKey. I'm ordering 10 of a single part from DigiKey. It still feels bad. Like, when you order stuff from DigiKey, you should order like a bunch. And so ordering just one part is a little weird. So, yeah. Temperature compensating, I don't really know if we're going to need to do that so much, as this thing is more of like a by feel. If this were like a like an oscillator, like an analog oscillator, I would be a little bit more concerned with temperature variations, because things get toasty inside of a modular rack setup. They can get warm. Yeah, and then a week later you need one other part. But those you can't anticipate. I've used we don't have a today command. That would be a good command to have. I don't want to maintain that. That's going to be really annoying. The title says what we're doing. We're doing mixers. We're doing an ice cream soda mixer. We're having a social. So like the mixer, in terms of temperature, what's going to happen to it? I guess these millivolt things can. Oh, the dog's back. Dog's back from the groomer. I'm indicated of that by the barking in the background. I'm like embroiled in this stuff, and then I have people coming in and like giving me a flipper zero. Here, have this project. This is another project. Let me just drop it off on your doorstep. God damn it. I'm like, when do I have the time? Sorry, I'm having a little bit of a crisis of usefulness. Everybody expects that the electrical engineer's time is completely everyone else's, you know? I got bitten by a Great Dane this morning, off leash, trying to defend my leashed dog with the fenced property I'm in. That sucks. We have a lot of dogs in this neighborhood, and it's kind of like we're off the beaten path. So it's like you could walk your dog pretty freely around here, but we're also a little too cavalier about leashes, and we know that the dogs run up at each other. And they run up at each other and they make a big stink, and it's like, dogs, calm down. You guys know each other very well. You don't need to be rolling up on each other like that. But it's very stressful to have, you know, because when a dog is behind a barrier, there's an anxiety that the dog gets. And so everything is amped up to 11 with dogs. And so you're holding a dog back on a leash, and you've got a fence, and the dog's going just because they're held back. And as soon as you let them go, they're like, oh, okay, hi. Like, it's like, stop making the problem worse. I created that barrier. One job is my dog's own safety during a walk. Yeah, but you should have the reasonable expectation that, you know, another dog isn't going to roll up on your dog and totally ruin everybody's day. I don't exactly have like an ejector seat for my dog. My dog is 40 pounds. I can lift her up, but that's difficult for me to do. So it's rough. And you know, we know all the dogs in the neighborhood. So when stuff like that happens, it's like, oh no, they're doing that thing again. But it's like, it's really bad. It's really not something that should occur. Yeah, you got a better control over the dogs. And we've actually been working towards doing that. We've been training the dogs pretty well to stay in an area and not roll up on each other. Okay, so what I'm looking at here are a bunch of example circuits. I don't think there's an extensive application note for this chip. Apparently you get better, this is so weird, 4-channel mixer using the SI2164. Each input is treated and shown as figure 1 typical application, summed into a single op amp. But you basically you can double up the amplifiers in order to get better effects of them. I don't know what that is. Luckily, the sweatshirt created enough of a barrier that I just got scraped. No punctures, no hospital. Damn. Yeah, because dog wounds are not to be trifled with. Since the gain in SS2164's amplifier is finite and well controlled, a significant noise improvement can be realized by connecting 2 or more channels in parallel. So I mean, those extra 2 channels that we have, we could maybe use one of these and do double channel mixing in order to get bandwidth or something. Right, it's the way that they latch and the way that they and the cleanliness of their mouth that makes dog bites pretty bad, and what it does to the tissues. Okay, so I mean, like, all right, we've got an input that we can emulate here, we've already got some of this circuit hooked up. This is frequency stuff, I believe. Actually, no, this might be the star of the show. So we might actually need to hook this up from our input, from our plus minus 10 volt input. We need to come into our amplifier. Now we got the amplifier to work, right? We put it through essentially that circuit. We built that on the breadboard. We need to make sure that we're doing the right stuff with the input though. I did not do the right stuff with the input. Now the 10 UF cap, I'm gonna leave off. I'm actually gonna leave off all the capacitors. The capacitors are there for filtration purposes, and while they are useful, we're just doing a test circuit. If we run into noise, that'll be a good example of running into noise. So let's figure this out. We need basically this in our circuit in the end. Oh wait, I need to revise this a little bit. Let's show the plan here. Let's come up with a plan. Let's come up with a plan. And let me undo all this stuff because it's not really that recognizable. So we need these channels to be amplified. Do we have like a proper triangle in here? There's no rightward facing triangle. I could use arrows, but instead I'll just have to draw them. Okay, fine. Fine. So what we need is an amplifier on each of these. Let's cut and paste it. I'll use a little cut and paste. And each of these channels, oops, 4, and then I need, what would that be? That would be like a voltage, that would be the mix, or level. I don't know how I want to represent that. I guess it's a potentiometer, so I might as well just draw a British potentiometer. Look at how British that looks. And that goes into here and into there. I could draw it as a knob and it would look a little bit better, but I'm gonna keep it like this for now. So those are level controlled. Oh, I need to do MS Paint, you know? Just make them default transparent selections. And then these would be like the mixer portion, but on the outset, they need to basically go into mixing channels. So left and right, like that, and then left and right, like this. And then we need to go into another thing, which is going to be the headphone amp. And somehow magically, we'll need to turn, so I'm going to do like, put a box here. Questions. And then, what was the part number again? Fat keys. No, that's not, wait, that's not it. That's this one. And it's TPA 6120. Six, 1, 2, 0. Headphone amp. And that takes a differential signal. So it would be, wait, hold on. L plus and L minus. It's going to be kind of hard to write down. L plus, L minus, R plus, and R minus. And those need to come in at whatever level with the control. So there would be another level thing. level, and then also pan. Two times in order to normalize the inputs. Where did the cool tubes go? We do not have the voltage to run tubes. That's something that was immediately evident to me about modular synthesizers, is that we simply do not have the voltage levels to be running. It's not, sorry, the current levels to run tubes, because you make the voltages, right? I can use 12 volts in, I can use 5 volts in order to make the tube level current, but the tubes are the heaters in the tubes take up too much current for a modular synthesizer. Transparency in MS Paint, think of the luxury. It truly is the modern age. So here's what I'm dealing with. I need to do two things to this amplitude. And I can avoid converting it to voltage until the very end. Let's figure out what goes into the headphone amplifier chip so that we can know that we're making the right thing. Filaments are like 10 amps at 3 volts. Guess you could have external voltage input for the tubes. Yeah, there's a pseudo, you probably know a lot more about this than I do, but there's a Noritake vacuum. They use vacuum, like VFL. Here, hold on. So Noritake knows vacuum tubes, but what they also have is they actually have a low voltage or low current VFL based tube amplifier. That's right, Korg has the Korg bought that in order to make them. Yeah, but it's Noritake's the original proprietor of the technology. But Korg, yeah, I think they worked with Korg. So I think it's like a dual, like it's both of them working together. Never heard of those? I wanted to buy a couple, and I think I had the resources at one point to buy them, but this is their technology, vacuum tech. But it glows green instead of orange. There are YouTube videos from a decade ago of people being unimpressed. Aw, man. Yeah, it's somewhere around here. I don't know. Anyway, it was a Noritake thing, and I was like, maybe I could put a tube amp into a... Now, we're not going to do a tube amp. We're just going to do the stereo hi-fi headphone driver. Oh, it had a vibration noise? That's very strange. All right, how do I know what goes into this thing in order to drive it properly? I know very little about this stuff. We're doing analog design today, which is its own set of stuff. You know, we got to deal... Eventually, I wonder if I'm going to turn into one of those people that can talk about, like, noise saturation and gains and stuff. I don't know if this is going to turn me into a weird beard audio nerd. It's scary that it might. VFD as an amplifier. Yeah, it's I don't know what they use the technologies that they knew of in order to create something that was like a vacuum tube, that operates like a vacuum tube, but at much lower voltages than your typical, you know, whatever they're called, triode. Wonder if the fluorescent material decays over time like normal VFDs. Might. We had a data sheet open about it a while back, but I don't have it anymore. I do not have it anymore. ESD ratings, operating conditions, 5 to 15 volts, load impedance, 16 ohms, and operating air temperature -40. Junction to ambient thermal resistance, we don't need to worry about that. Electrical characteristics, input offset voltage measured differentially with VCC of ±5 or 15 volts, 2 to 5 millivolt offset. Rejection ratio, common mode input, supply current. I'm probably gonna have to do a lot of equations in order to run this thing properly, right? Near my house, there's a water vending machine that has a VFD 1602, and it's so sad. The segments are so dim. I guess it's outdoors. That's crazy. Yeah. Output resistance, an open loop is 13 ohms. I don't really care about that, the output stuff, because this is dealing with all the output. It's the input stuff that I'm really worried about. Input offset voltage drift, 20 microvolts. No, I'm not worried about that either. I just want to see, what do we need in order to feed this thing properly? At the maximum volume, what is that circuit going to look like? And this is all distortion stuff. Yeah, because it's a fluorescing material. So if it's in like heavy UV from the sunlight, that definitely degrades it faster. Actually, I'm not sure. I would think it does, though, because sunlight degrades everything. It really isn't not good for stuff. Audio precision measurement output. This is their measurement information. Current feedback amplifier with differential inputs and a single-ended output. Current feedback results in low voltage noise, low distortion, high open loop gain throughout a large frequency range. And that can be used in similar fashion as a voltage feedback amplifier. So actually, the transconductance amplifier that we're using is perfect because we can then feed it in conducting mode, I guess, into this stuff. I think. Yeah, that's so many memes from that one video. Sun is a deadly laser. You could make a religion out of that. Because the power supplies for the two amplifiers are available separately, one can be turned off to conserve power. We're not worried about that either. Note, the information in the following application sections is not part of the TI component specification, and TI does not warrant its accuracy or completeness. TI's customers are responsible for determining suitability in components and their purposes. Customers should validate and test their design implementation to confirm system functionality. In many applications, the audio source is digital and must go through a digital to analog converter, DAC, so that traditional analog amplifiers can drive the speaker or headphones. So they happen to have a DAC, a PCM 1792, which is an oddly familiar DAC. I don't know if we've actually built something that uses that DAC. I feel like I've heard that number before. I mean, there's the 1792, there's the 1972, and the 1972 is a 15-volt volume control through-hole thing that I have. Very considering using that in this design just because it's funny. It's a completely obsolete part that I could actually use in this design. Here, let's get one of them and look it up. All the analog shenanigans that I can get up to with these modular synthesizers. I've had these things in my drawer for longer than some of you have been alive. That's not it. 74HC. It's AG75. I don't think that's it either. It's this giant chip. Hold on, let me find it. Might be these. Nope. LM19. Oh yeah, LM1972. That's it. LM1972N. Micropot, 2-channel, 78 dB audio attenuator with mute. This is just a weird chip that I have. It's just a dual attenuator, which, you know, I would, if this were a smaller chip, but if it were more modern, maybe I'd consider putting this thing as the, oh, see, there's even a pan control. It's like bespoke for this purpose. I think in the research project, they were trying to use these in order to attenuate the signal coming back from the optical detectors and perhaps computerize calibration control. Of course, nowadays you just throw as many channels on it as possible. You don't have to conserve and multiplex as much anymore. Step scheme for the LM1972 Microsoft figure. This tenuous step scheme, however, can be changed through programming techniques to fit different application requirements. I guess this requires a CMOS signal. Yeah, it's got like a logic on it and everything, but that would have been a consideration for this. We like to keep the digital stuff away, though. Right, put that thing around back and move this over. I have an ancient 8-bit DAC from 1970s era waist scale. Oh, cool. It's demonstrably one of the technologies that has where when you go back in time, you don't get higher quality ones. It's like, this is an 8-bit DAC from the 1970s. It's useless. Nowadays, we have a $1 DAC that does way more than that could ever even imagine. So it's the TL505CN. Just take a quick look at it. TL505CN. We're very distractible today, if you haven't noticed. Oops. Oh, so it's like nuclear hardened. Look at that beast. Analog to digital converter. Oh my God. Comp out, zero gap, integral stuff on it. They probably give you a picture of the die. Usually on these older data sheets, they'll give you a picture of the die, like you're supposed to get some kind of information from that. Oh, how to hook it up to a microcontroller. This is the latest in 1970s technology. Digital numbers. Get this thing out of my face. That thing's ancient, useless. No, we're going to be using this part here, and this part here, what in the world does it even require? TMS 1000? I don't even know. You talk to me like I should know these part numbers. Digital audio is fed into the high-performance DAC, the PCM 1792 is Burr Brown product from TI. That's 24-bit stereo DAC. What are the parameters and what's going on here? It seems as though we are feeding it into a transconductance amplifier, right? Why are we doing that? If we're turning it into voltage through the 1 kilo ohm resistor and into whatever the hell is going on here, I really need to figure out how this stuff works, because they're talking about this stuff being in current levels. So instead of it being a voltage level, you're moving more electrons through, more and less electrons through, in order to make your waves. And so the schematic is a little different, the techniques are a little different, but apparently there's way less noise. So how do I design in this space in order to effectively feed this thing the signal that it wants to get? We have 10-volt peak-to-peak signals coming in. Let's just assume that we need to be catering to control voltages inside of a modular synthesizer. So modular synthesizer, Eurorack in particular, is supposed to be this walled garden. There is nothing you can do wrong within the walled garden. I can take an audio signal and I can plug it into a CV signal, and everything isn't going to fucking explode, because every time we see a design that allows for the 800-pound gorilla to flex its legs, we see that design blowing up in the face of the designer. I'm not pointing fingers and I'm not naming names, but everywhere that a design has allowed some kind of wiggle room or some kind of an unknown within this walled garden, some kind of a unique thing that sort of bucks against the standardization, we have seen carnage. So what we need to do in the design of this mixer is to make sure that we are not allowing anything like that to occur. Obviously, on the physical side, we are going to be labeling things to within an inch of our lives. I don't think I'm putting in a shrouded connector. That's kind of a lot of hassle to have that many through-hole pins. There are surface mount shrouded connectors, but that opens up the field to somebody unplugging their module and having the connector rip up a bunch of traces. I don't want to do that. Instead, I'm going to have 5 pins in a row and a lot of labels on that thing to make sure that people can't plug them in wrong. I can't account for people who are high, because people will plug it in high, but at least I have a little bit of that safety there, and just saying, like, this goes here, you know, and having some protection diodes on it too. We're not going to use 5 volts. We're only going to use plus minus 12. That's all well and good. So in that vein, we have to make sure that if somebody plugs a plus minus 10 volt signal into any of our plugs, it's not going to ruin our day. That begs to wonder what's going to happen to L and R out if somebody plugs in. I mean, it has short circuit protection, so I guess if it gets connected to ground, it should be okay. But if there's a heavy differential in between some of these pins, I guess this amplifier needs to be tolerant to the signal. And I think it is. Let's just check. Let's double check. Crosstalk, total harmonic distortion, common mode input voltage. Typical 11, max 13. Supply current of each channel, 11 to 13 milliamps. Input offset voltage drift, input resistance, output resistance. So the input resistance would be 300 kilo ohms. Common mode input voltage. So VCC of 5 volts, it's 3. And if VCC at 15, it's 13. So at 12, what is it? Projection ratio, 75 dB. Input offset voltage measured differentially. So VIO, input offset. So they want 2 to 5 volts offset max, but that's 2 to 5 millivolts. Huh. So what are we doing a plus minus 3 volt signal? No, it would be common mode input voltages. 15 volts, 13. It would be somewhere around 12. The hidden gorilla theory of electronics. Think of the electrons as little tiny gorillas. NTSEB, nothing too strong ever broke. Well, I want to make sure that we don't blow this thing up by plugging the wrong stuff into it. I think we'll be okay, but I don't know. Because it's like at 15 volts, we got 13. At 5, we got 3. So at 12, we'd have 10, which I guess kind of makes it good. I don't know. I got to get one of these chips in so that we can just hit it with numbers. And then the inputs to this thing are differential and current based, if I'm correct. Right channel output, left channel input, positive input, and negative inputs. And then, so high slew rate that prevents odd order distortion anomalies. The second feature is current on demand at the output that enables the amplifier to respond quickly and linearly when necessary with risk of output distortion. When large amounts of output power are suddenly needed, the amplifier can respond extremely quickly. None of this is helping me. Third feature is a gain-independent frequency response that allows the full bandwidth of the amplifier. 4 to 20 milliamp synthesizer. TPA 6102's current feedback AB amplifier architecture. That's just the architecture. Yeah, this is getting into like circuit level design that I'm not totally familiar with, this whole amplitude thing, instead of it being voltages. Everything is voltages in the synthesizer until you get to this stuff. You know, they're all stupid and crazy. Current feedback results in low voltage noise, low distortion, high open loop gain through the large frequency range. It can be used in similar fashion as voltage feedback amplifiers. The low distortion of the TPA, blah, 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 signal noise ratio, 128 dB. And then we can turn off power supplies. Typical application shows a complete circuit schematic for such a system. The digital audio is fed into a high-performance DAC. The PCM 1792 is a Burr Brown product. Okay. And then they're just like, whatever. Detailed design procedure. The output of the PCM 1972 is current, not voltage. See, this is to our advantage because we are using the VA 2164, so we're in current space. How do I make opposing current with the using all this stuff? Current, not voltage, so the OPA 4134 is used to convert the current input to a voltage output. What? Wait. Why did but the input to this thing is current. Is it not? Convert, let's see, hold on. The output of the thing is current, not voltage. So the OPA 4134 is used to convert. See, I mean, if we're doing, we could basically do exactly what they do. We could just take this whole part of the circuit and just cater our own numbers to that. We could just move the numbers around until they work with the headphone amp. But I thought this thing was already operating in current space. So wouldn't it be a more direct connection? Because our individual dimmers operate already in current mode. That's what these are doing. And so they have the transconductance set up here, turning it back, which is what TI is doing. So we could basically just insert our stuff right here and it would work in the same manner. But that's a lot of op amps. That's a lot of op amps. That's so many op amps. And then in order to do left and right control, we would have to figure out how to do that. Oh God, how would we do that? Because we have multiple amplifiers in the stages here. Man, my brain hurts. This isn't that complicated, but I just want to make sure that we're doing the right thing. So 12-volt operation of power supply, differential voltage source, be transparent to the user. All right. The output of the PCM 1792 is current, not voltage. So the OPA 4134 is used to convert the current input to a voltage output. Now, if we did that and we wanted to have more of the VA 2164s dimming that, you know, doing an overall volume control, why would we convert it into something else? We would need to actually take it into the second set of amplification. So it would basically be this thing right here. It would be, you'd have your transconductance amplifier. This is all going to be very wobbly drawings. Welcome to the wobble zone, where we draw things in a wobbly way. Things will continue to wobble until morale improves. So we have our input signals coming in here, getting mixed, and then it would go to another transconductance amplifier that would then do volume. And then that would go into the headphone amp. Or it would get converted to voltage. To voltage, and then it would go into the headphone amp, into the amp. This channel is underrated. I just subscribed. Well, thank you. I appreciate that. It would be, hold on, wait. Where's the cat? Somebody put the, I'll do it. Is it jam? Yeah, there it is. I need that in the snipping tool. This is, I've never done this kind of design before. Hey, what's up, Flask? I have never done this kind of design before. Where's the snipping tool? You know, everybody thinks they're gangster until the analog design starts coming out. Everyone's got a plan until analog design hits them in the face. I really need a larger version of that. Hold on, I think I can click on it. Oh, I have to be in Twitch to do that. All the way back to Twitch, I can click on the emote. Oh, but it's got a dark background. Darn it! And I have to hover over. Open image in new tab. Yeah, no, it's gonna be tiny. How's it going, Flash? Yeah, so all right. So we're working on like analog design and figuring out how we can kind of minimize the amount of amplifiers that are going into this thing. The current setup that we have on the board is something like this. We haven't mixed the channels yet, but I'm trying to figure out how we can feed our headphone amp, our hamp, if you will, a differential signal. So I guess that's probably going to need to have an inverting and non-inverting current to voltage. And so that gets a little clown nose on the end because it's inverting. So if that's the case, I guess we have everything that we need in order to design this. And I don't need to worry about what values are what, because I will be Well, okay, so adjusting the resistors on it and also figuring out what I'm going to be using as a control signal into the various stages. And so the other one is normalize RNL. And it's possible that instead of a single driver coming off of these, we could possibly have a double driver to get better something. they said something better something, double up the driver. And so I said, you don't got to tell me twice. I'll remember that to the grave. Double. And then I guess the mix control could have, like on the left channels, I could have an additional resistor, like one extra bias potentiometer that would add or subtract from that. Doink. A lot of question marks. A lot of question marks going into this. So if our input, we know what our input amplitude is going to be. I don't know how we alter that. I don't know how we alter that amplitude. If it's all well and good, I guess we could just put it into the multiple things, but like they're not going to necessarily be balanced. They're not going to necessarily be properly controlled for 10 volts plus minus. Maybe they are. Because, I mean, this stuff is made for modular synthesizers. The V2164. So what they suggest in their data sheet, one of these anyway, where is that one? Somewhere within the data sheets. Oh my God, what the hell is that thing? Get away, get it away, get it out of here. I'm scared of that. That's a low frequency oscillator. There's a lot of cool circuits that involve this thing, and we can look up other mixers too. We can try to get an idea of what other mixers are doing. I didn't mean for this to be a completely computer stream. I would like to switch over and do some stuff on the breadboard, but without a plan, we're just somebody who got hit in the face. We don't have a plan, so we need a plan. So this is a 4-channel mixer, and it's as easy as putting your signal through a 30 kilo ohm resistor and a 500 ohm resistor going to ground. And so 30 kilo ohms, something to do with the impedance of the V2164. We are using the V2164, so we don't need like a different resistance value there. We can pretty much just follow this. And so this will mix VCA, sorry, not VCA. This will mix like control signals. It'll mix audio. It'll do it all well and good in the voltage levels that are required of synthesizers. I mean, to be fair, like I guess with the headphone amplifier, we're going to scale it to control voltages in case somebody wants to mix control voltages, but it's not going to be doing control voltages on the outset. It will be scaling them down to headphones. That's just how it's going to work, because I'm not going to hit somebody's headphones with 10 volts. I'm just not going to do it. You just can't get me to do that. It'll be capable of getting a control voltage in, but to what end? It probably won't do anything with the control voltage, right? And if that's the case, I mean, we're fine just taking this over to current space. But like V out from the OPA 176 here, that's going to also be a control voltage, because the example here is audio or control voltages. So this is going to be plus minus 5 to 10 volts. And if we use another one of these and we double up on the drivers on it, thinking. Yeah, I guess that's just going to be what it is. That's just what it is. And there's no feedback, and then we have it in A/B mode. So we should hook something like this circuit up and see if we can create our end-to-end stuff. And then at the outset here, we need to have 2 amplifiers. One of them will be like this, and the other one, we flip that plus and the minus so that we actually get the opposite output signal. It'll be an inverting, I guess you call it an amplifier still. It'll be an inverting transconductance amplifier. or no, that one's inverting. We need to make a non-inverting transconductance amplifier. So it'll be the same thing, just flipped on its head. I think that works. I hope that works. And then we'll be able to take those two signals, and that will then go into the headphone amplifier directly through a resistor. So we need to figure out what that's going to be. Okay. I think I've got an idea. I think I've got a plan of an idea. What is it? There's rumors of an idea of a plan that's going into this. So we're basically taking, is there another mixing thing? Oh, look at that one. Voltage, that's a basic VCA. Yeah, that's pretty good. That's all the same values of stuff. So we'll just alter the schematic a little bit here. So I'm gonna take this picture and a little snippy. Snippy to clippy. And we're gonna take this into our design document, our sacred design document that we are not going to besmirch in any way. This is a very important document. This is, you know, patent level stuff that lawyers are going to be going over when we finally have to fight one of the synthesizer designers. So we need to make sure that this is a completely mature document that can be, you know, passed down to future generations of engineers. Paste. All right, so this one here. And then we're going to chop this up and we're going to add another amplifier to it. Well, another couple of amplifiers to it. Because what we're going to do, well, actually I need two of these, but I'll just take this and I'll move this out. Oops, I guess highlight doesn't persist because MS Paint is just a beautiful piece of software. So take that out to there. Let's get rid of a lot of the excess stuff on it for now. And I'll take another one of these guys. Place it right here. This says nothing for the normalization of right and left. We don't have that technology in here yet. Probably can move that a little closer because I'm going to snip away all of that stuff. It's a little close to my other notes, but whatever. So all this stuff goes away and we chop it up. We start connecting things to each other. So in this case, these two are going to be connected. Oops, that's not the line tool. That's not the line tool at all. Dun, dun, dun. Like that, and like that. And then, let's see, we'll do that to that, and this to that. And then we need to do the weird crossover, which is easier if I do, wait, did I do that right? No, I didn't. Nope, didn't do it right. It's actually, this one goes down to there. It's going to look like crap when I'm done. This one goes straight over. And then this one goes up. It's going to look terrible. Whatever, you get the point. Make sure I put dots on things. Yeah, that doesn't look right. Now, redo the whole thing. And this time we just do you go to here, you go to here, you go to here. No, you don't. Wait a minute, that's wrong. Oh yeah, because these are doubled up, right? Double it up, cross it over, put it directly over. There. We get a nice pattern out of the whole thing. Look at that, it's beautiful. And then all of these get connected to each other. And we have to figure out what that control circuit's going to look like. We'll just do it with the line tool. I said, why is the line tool so squirrely about being connected? Weird. So all four of these actually go to the same thing. Because that's the overall volume control. And I guess left and right, I mean, there could be an overall left and right bias that I connect to this thing, but I don't know if it, I think if you're already biasing the left and right, you're not going to need it. So let's just continue on with what we're doing here. We're coming up with a plan, then we're going to test the plan, and the plan will probably alter what we end up with. This is important work we're doing. And then I'll go to volume. Too thick. Hey, what up, wonky robot? What's going on? We're coming up with a plan. We're trying to come up with a plan anyway of what we're going to test in order to get this mixer together. This mixer is not supposed to be a very big project. It's supposed to be relatively simple. But, you know, the way things go. So we have channel 1, which is this one and this one. See, well, we'll do mix 1. Mix 1, and then this one and this one are mix 2. And that's R1, L1, R2. We are not zero indexing our arrays here. R1, L1, R2, L2, and that's plus minus 10 volt compatible, but it's really supposed to be plus minus 5 volts. We'll see what happens with this circuit, because we can build this right now. We can put this together once we figure out what the knobs are supposed to be doing with the voltage outputs, because I think it's very, very low control voltages. I think they're very small voltages. We'll have to, let's just like look up a mutable instrument circuit, see if what Emily Gillette is doing. She probably mixes, what do you call it? Mixes the voltages with control voltages, so we can see what the circuits are that are allowing the control voltages onto those pins is, what the ratios of those are. So now we're going to need 2 of these, but I'm going to need these to be in a differential configuration. I don't know how transconductance works. I do not know. It's just silly, wonky magic to me. So what I'm going to do, and I guess in order to communicate that this one is flipped, I will take, I'm not going to, well, actually, here's what I'll do. I will flip vertical, the plus and the minus, and then just to make everything look completely ridiculous, I'm going to take this whole thing, except for the ground lug, that I will keep in that orientation. We're going to flip this vertically, so that the op amps pluses and minuses are properly communicated, even though the text is now upside down, because we are putting this into an inverting scheme instead of a non-inverting scheme. So this is still going to go to ground. It's going to be referenced to ground, but in the opposite direction, is my theory on how this works that I don't really know the validity of. So we'll be able to potentially test this out and see whether or not I am full of nonsense. So let's see. So we got 2 of these, and then those will go into the headphone driver. And these are mixed channels, so they can just simply go to just a big bar out in space. The space bar, if you will. Do you get it? Do you get the joke that I just made? Simple. Never do 4-way junctions. Never, never, never. Always do 3-way junctions with your schematics. That way you're not confusing an engineer that comes in and looks at it, and maybe you're missing a dot somewhere. Maybe I'm missing a, oh wait, I shouldn't be going into that pin. You know, you might be missing a dot somewhere, in which case never having 4-way junctions means that this does not mean that they connect to each other. What is the VCA for a chip? The V2164 from Cool Audio. The other option is the SSI2164. Anything with a 2164 on the part number, basically. Never do four-way junctions. They are poison to your schematic drawing. Oh, this could have been. I should have lined it up a little better. That's fine. And then that all goes into the, I'll do a little box for it because it's essentially a box. That one is called AMP, TPA 6120. And yeah, you get it. I can do a giant curly brace for all of this. The biggest curly brace ever. Very cool, pun intended. Yeah. Insert humor here. And that, of course, goes to the headphones. Okay, so that seems to be a little bit more of a plan. I don't know if we need another stage of amplification, though. More amps? Question mark? Because we've turned it into voltage here for the TPA 6120. I don't know if we've done anything to make it not, like, to put it in the right volume level. Because, like, we could still be plus minus 5 volts on the output of those amps, which is not what's coming out of the DAC that they have in the other example circuit. So we can't copy the example circuit exactly. But in the example circuit, they said this is current-based. So we need to turn it back into voltage-based. And I'm like, neat, that's almost what we have. It's just weird enough that we don't know what's going on. Where is that? That's here. So they're using transconductance amplifiers in the OPA 4134s out of an audio DAC that's already in current mode. It's already doing current instead of voltage. That is the technically correct symbol for headphones. Yes. I like how they have just a picture of headphones. That's actually, believe it or not, being as stupid as we are and unviable as a species because of our stupid electrical meat brains that just cannot seem to do the right thing ever. I actually leaned into that, and they put picture of headphones on their circuit. I am getting this chip for that one reason. They just have a picture of headphones. They say, here are a generic pair of audiophile headphones, or of higher class audio headphones. And I went, monkey brain like that. I buy now. I think that's all it took. That's really all it took. So the values of this thing are all 1K going into that final stage. How does that even, why does it even work like that? What does that? And this thing does current output, so it's easy for me to put it into our complicated mixing. Go back to our schematic now that we've got all this information down. Mix 1, mix 2, and then in mix 2 there would be bias. Mix 2 has bias. Or no, it would be L channels of mix 2. So there might need to be like a potentiometer here. But all that would do is lower the amount of voltage that goes into there. So I don't know all that would be able to do. And I guess the solution around, if your right channel is too high, how would you, Filtering for DC killing. I'm not sure if you need to do that. I don't think you need to do that with this. Because the original circuit is a mixer that works with control voltages and audio. So we're just going directly from that. So control voltages will not kill this circuit. Audio will, of course, work with this circuit. This thing probably won't be able to make control voltages on the outset. This thing probably won't be able to make control voltages. So that would put it into saturation. But, I mean, I don't know. And then there'd be another set of op amps on this whole thing that would do clipping, which I don't know if we're going to be able to do, given the scheme that we've got here. But let's start hooking this thing up. We can hook this thing up and get sort of more of a representation of the circuit. We're basically going to make like one channel of this. So I'll take an LR or just the two audio input jacks. We'll put the two conductance amplifiers on the two voltage controlled amplifiers on those two channels, and then we'll combine the output and we'll put two more conductance amplifiers on those, and then we'll put those into the TL074. Whew. Okay. All right. I think we have somewhat of an idea of what we're going to build here. That just leads us down to our breadboard circuit and getting everything together. And we're going to use TL074s. I'm not going to use the OPAs because I don't know if I have them. But all this stuff will then translate into surface mount, and then we can get that into our board design. So I'm going to rip up the entirety of what we did last time. I'm not going to like it, but I'm going to do it. Op ampception. There's so many op amps in this design. It's incredible. I didn't expect this to be, because like if you're mixing just with the TL074 and you don't have the voltage controlled amplifiers, it is not a difficult circuit. I mean, like mixing with an op amp is so simple. But we decided to go a little bit more complicated and high quality. And we've seen this in like mutable instruments circuits. You know, the mixing is just simply done with resistors. You just have resistors there. And so you could have all of your different channel resistors be potentiometers, and they could lead into this singular op amp. That'll then invert the signal, and then you turn it back around so that it's not inverted, so you don't deal with phase issues on your outputs. That's it. That's all it takes. It's two op amps to make a mixer. That's what a lot of these more simplistic mixers are. The op amp can take up to 10 volts, plus minus, so it's totally easy to just put all of your inputs into an op amp, give them all their own resistors, and that'll give you control over all of your individual channels, and it'll be a very simple circuit indeed. That's where I would have liked to go with this, but because we need dual control over left and right, we then need a control voltage. And so we make a control voltage using a potentiometer. The control voltage feeds two channels that can be turned up and down. So the complexity is, it's kind of snowballing in this case. But I think we've settled on a design of sort of the minimum stuff that's going to make this thing. But that's where the breadboard comes in. So let's get to the breadboard. I'm gonna open up a seltzer. I got a seltzer sitting over here in a can. I got a can of seltzer that's waiting for this. We just have canned seltzer today. That's all. I'm just making a big deal out of it. Ah. All my audio level stuff. All right, so where's the pinout of my pinout? Is it okay? Is it safe? So, oh, this has pins marked on it. Oh, but this is for the SSI. So the SSI 2164 has some more circuits in its data file, or in its data sheet. It's got some nice stuff to look at. Temperature compensated exponential voltage to current. This stuff is way too bubbly. I'm gonna die. I'm fine. 1 volt per octave in, but then what comes out of this thing? Current comes out of it. That's weird. I guess this is similar to what the Emily Gillette circuits were doing. But when things turn into the current zone, I get confused. Did I end up with pirate software modes? I like pirate software. I looked at some of their stuff when we were talking about them. It's funny, there's like a whole group of these people whose like brand names for their social stuff, you know, like Tomato, pirate software, you know, these people who are trying to like get people Googling stuff in order to sort of build up their, all right, we're not doing the faces today, are we? Because those are really distracting with the speed of my chat. Don't do it. But yeah, all right, so there's a bunch of designs in here, but I don't think we're going to need the SSI 2164 data sheet. So I'm going to close that and find the pinout. Here we go. This one actually has, oh, it does have pin numbers on it. So we can just follow this. We can just follow this. I don't think I'm going to do the decoupling 0.1 UFs. We're going to be a little bit less clean about our production of this thing. but we need to find 30 kilo ohms and 500 ohm resistors, and then I need a 30K for the output. We will hold off on doing that yet. Well, no, we can hook up this entire circuit. We had most of the stuff testing last time. So yeah, all right, let's take a look here. And then the other thing I want to figure out is how to do that VC. How do I do VC with a potentiometer? Actually, let's figure that out now before I even start building the circuit, because I'm hoping to put it up to a 10 kilo ohm potentiometer. But what I basically need is a V2164 design, and we can look at mutable instruments designs in order to figure that out. So let's figure this out. Let's close this. I'm already beyond this stuff. I'm way beyond this. That's the singular op amp. I have some of those on order, I believe. The proper ones so that I can fix Dave's thing. Yeah, we don't need any of this stuff. Close it all. Now we're at mutable instruments, and here we have blinds, which is a voltage-controlled amplifier mixer. It sort of mixes down the line as you go, and if you unplug something, it'll send it to the next thing. So this one's schematic. This one's Veils. Veils is a little different, I think. No. Veils is actually what we want. So what's happening here is we have a signal coming in J5. It goes through the conductance amplifier, in this case 50K and 510 ohms. Veils is audio. Yeah, so this would be the audio mixer. So 50K and 510 ohms, I guess Emily Gillette settled on, goes through the transconductance amplifier where it becomes current control. It then goes into another 50K and 100 picofarad. That's to filter out super high frequencies, and then the 49.9. I don't know what exactly it's doing there. It's some kind of a frequency related thing, but that turns it back into voltage. When it's back into voltage, it then goes through a couple different amplifiers. And so the beginning amplifier is this one. We have 5.1K in unity gain. So it's not actually amplifying anything. It's just buffering it, I guess. Because I guess it's inverting here, so we're inverting it back over to normal frequencies, to normally oriented frequencies. So you don't get weird phase variance out of it. Up here with the LM324, we actually have a clip indicator. So that'll tell us if there is, if the LED is super bright, then it says, you know, we're clipping. If it's dim, we're within our audio levels. And I want to put this on my circuit, but it requires its own op amp. So I don't know if we'll be able to do that. I'm going to burp. God, it's the problem with seltzer out of a can is that it's way too fizzy. Too fizzy, I say. And then the special thing about Veils is if you don't have anything plugged into this channel, it will then feed down to the next one. So all of these audio levels, I guess, are being pushed out. And if you want to mix them, you can plug into the channel below where you're inputting. So you can have the one channel and then the channel above it mix with each other. And then that's going to be cut off when you have an output plugged in. So I guess if you had 4 layers, you could plug them all into stuff and they would be isolated 4 layers. But if you had 3 things coming in, you could plug into that third and you could have an isolated 4th thing by plugging into the 4th. It's, yeah, I guess that's how that works. So that goes down, that's OPA goes down to, where does it go down to? Right here where it's mixed in. And it's mixed in Unity. So it's just directly sent into the next piece. All right, so that tells us a little bit about what's going on there. I have never read anything about Veils. I'm getting this all from the schematic. Just by looking at the schematic and looking at what the amplifications are and stuff like that. So, yeah, I guess I got it right. 5.1 and 5.6, I guess it's getting de-emphasized on like a very small scale, because the ratio of 5.1 to 5.6 is not that much. Maybe it's just to take up some of the transmission stuff or whatever it's about to go into next. AREF plus 10 coming in to an unplugged CV input. with a potentiometer. Well, there's two. One of them is doing the biasing. Well, no, see, this is reference. They're both hooked up to reference, so those are two separate things. So this one is coming in and it's mixing in over here. You've got another amplifier with an analog reference going into it. So analog reference being biased by another control here. What the heck is this doing? And then that one has the, I guess, like an indicator LED on it. And it's indicating 68 ohms on a 2.5 volt with a 1 oh, sorry, they're both 1 mega ohm. Sorry, 1 mega ohm on both of these. So these are unity. Those are current biasing. And you have 1 M on the analog reference. What does it all mean? Whatever's coming in here, we are mixing with 2.5 volts as a reference. Sorry, negative 2.5 volts as a reference. I see. So one dictates the behavior of the other one, whether it be linear or logarithmic. This is a roundabout way to do it, but I guess it's got to be done. What I'm trying to get is an impression of what the control voltage looks like for this V2164. And if we are shifting it on 2.5 volts, but then we have LEDs in both directions. So it's biasing the range of the LEDs over, and then it's just throwing it in. I think it's a, so is that range negative 200 millivolts to 3.3 volts? I think that's what the data sheet said it was. It took a little bit of spelunking in order to figure it out. Let's dig in. We've got our heels fully dug into this thing, so we need to figure out what those voltage levels are that are going to give us our biasing. Because, yeah, this is tolerant of whatever voltage you're putting into the whole thing, but that's not actually where it adjusts. It's tolerant of it. It's not, it doesn't, yeah. Noise, headroom, total harmonic dispersion, channel separation, slew rate, input bias, output bias, current, nanoamps, input impedance. Would this be the number that I'm looking for? 1 to 8 millivolts? I'm trying to figure out what the control voltage is actually going into this. And I guess we can measure it with the scope. And that way I can figure out what electronics I need on these things in order to make sure that I'm fully in control of the volume over there. Is there a VCA that uses, okay, so let's, V2164 VCA. And I'm just going to look at simpler circuits that have not been gone over a million different times. Quad VCA, they're doing that. They got this up here. This is offset, and then the other one is being compared. Uh-oh, this is going to dox. Don't you show them my, oh, there it goes, showing you my email. So only wire one of the VCAs to make it more readable. Everything in the blue except for the trimmer pot, blah, 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 blah. I don't even know what's going on here. Dual VCA, control voltage, offset. So the VCA offset 072 type op amp, and it's being compared to, that doesn't really help me at all. 100K to 39K, we've seen this before. In fact, we've seen this in mutable instrument circuits. 100K to 39K is a 1/3 ratio. So our plus minus potentially 10 volts is being taken to plus minus potentially 3 volts. So we have a 0 to 3 volt reference maybe? That might be what it is. Although I'd like to see a more professional circuit. I'd like to see a slightly more professional circuit around that. Hajiwo's done one. How embarrassing. Yeah, that's how I feel pretty much all day. That's how I feel. So what did Hajuo make? I trust Hajuo. Translate this into English, which is moderately functional. Variable response curve for modular synthesizer. So this has a curve adjustment on it. V2160 dual VCA. Let's take a look at that one. The response curve is fixed at exponential. This is modules an upgrade to the version of VCA Rev 2, the second of the LM137s. Okay, so this one is, can we translate? Hey, Google Translate. It doesn't want to. We'll never know what's going on. I actually do need to read this, so translate to English. There we go. 24th of the homemade modular synth. Hajuo's stick is that he creates all of these DIY modules himself, and he makes them cheap. He does them with as little cost as possible. So it's always fun to find it's always fun to find a Hajuo circuit that does what we want it to do, because we know it's going to be absolute bare bones minimalistic in its function. However, this isn't just simply a knob that controls the amplitude of the output. This is a knob and a CV that controls the amplitude of the output. I would love to give Julian the capability of controlling this thing with control voltages, but we simply do not have space for the connectors. There just is no space. Unless I put these only to CV. I could put another Thonky Kong on that, and then it would be a stereo mixer that operates with control voltages, and we would have so much space for all of our chips to go on the bottom of this thing. No, we don't. We don't have any space. I'm going to have to really like pull out the stops on all the tricks that we can do in order to make this thing. But I don't know. We'll get there. That, or in the end, maybe he's just going to get just a simple TL074 mixer. You know, it's like I put 3 TL074s on the back of this thing, and it's a mixer now. Hey, hooray! As the number of modules I make increase, I wanted to play a song using only my own modules. However, I didn't have a VCA module, which is the basic component. I decided to make one. Homemade module is designed on a single 5-volt power supply, but it's more convenient for the VCA and VCF to run on plus minus 12. That's what we're doing. We're keeping it 12 volts native. All of the chips that we're using can use 12 volts. Although it will cause the system to lose consistency, I decided to use plus minus 12 power supply this time. I used the V2164 IC. There are many types of 2164s, but in Japan, the V2164 is available from Akazuki Electronics. For us, they're available from Cabin Tech. Cabin Tech has all of these chips. These are, unfortunately, when you get into these synthesizer chips, they are harder to find. You can't just find it on DigiKey because they're not doing that volume of sales. They're not selling that many of these things, even though synthesizers are fairly popular. The reason they're so expensive is that sourcing these components requires you to go through different avenues. So sometimes you can find a full bill of material from DigiKey, but other times if you're using the convenience of using some of these eclectic chips, you have to go through very specific suppliers. And in this case, Cabin Tech luckily has all of our backs, our collective backs by stocking these things. To be honest, I've been avoiding making modules that require minus 12 because I don't know what negative potential means. I'm not good at analog circuitry anyway. Again, negative potential is just a shift in what you're thinking about. If you think of electrons flowing around, the potential for electrons to flow from one thing to the other is all we're talking about. Voltages are potentials. So from ground, electrons can flow to negative 12 because it is a lower potential. And if you really want to think about it in another way, you can think about just shifting the number line. So all ground is a voltage level that we decided we call 0. And so calling that 0 redefines what was originally ground as being negative 12, and then positive 24 volts is now plus 12. We just shift the number line. All you got to think about it as. It gets a little bit more complicated when you get through like the nodes of the circuit and you're looking at stuff like that. But for our intents and purposes, we have not had to deal with anything too crazy in terms of plus minuses and designing specifically for negative 12. Whatever we're doing for positive, we're doing for negative. That's all it is. It's just potentials floating around in space. I hope that helps somebody, because seeing it in writing right here is the same thing that you guys have been saying ever since we started down the road on these modular synthesizer circuits, is that, you know, I don't understand negative. Well, it's not hard. I hope some people can learn to think about it the way that I have. 3U, 6 HP. Wow, look at all that space. That's so much room. We have 2 HP. Power supply, 25 milliamp or less, blah, 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 blah. Okay, we don't need to worry about all that stuff. Knob 1, offset. Knob 2, offset. Channel 1, CV in, range 0 to 5. Channel 2, CV in, 0 to 5. And then channel 1, signal in 2. Out 1, channel 1. Out 2, channel 2. 0 to 12 volt. Same circuit and performance. If you lower the offset, the volume will be 0. So what is the offset and... That is a lot of electronics sitting there. Oh man, I shouldn't pick at my face. I had a little, like a pimple under my beard. And so naturally, the way to properly care for a pimple under your beard is to pick at it until it becomes a large open wound. I am dumb. If there's no CV input, the volume is controlled by knob 1, knob 2. If the CV input, the volume is controlled by the CV. CV input range 0 to 5 volts. And when the CV is 5 volts, the volume is value set by the offset. Volume is the value set by the offset. All right. It can be used as a simple signal attenuation or signal amplification module. Since it's dual, we use the send return from guitar pedals. Okay, so we don't care about production cost. Hajiwo takes all kinds of shortcuts in his designs. He ignores the cost of connectors and PCBs. He just talks about the chips. I guess panels, 100 yen. I don't really care. I'm glad Hajiwo keeps them cheap. You can do this, although the performance of the different 2164s require slight alteration to your input resistors and stuff. So in this case, 2164. Okay, this is a nice simple circuit. The only thing that's a little strange about it is that our ground point is being controlled. So the offset can become the volume knob. So at unity gain, he has 0 to 12 volts coming in here. He's 39 and 39 on the op amp. And then the semi-fixed resistor for pre-offset. There's a 1 kilo ohm potentiometer. Oh, what does that mean about the voltages that this thing gets in? Let's see if he explains that. Maybe he just has it in here. Because what I'm doing is I'm trying to look at the circuit and figure out, like, how can I make a single volume knob control this thing from low to high volume, and I just don't know. Like, I read the data sheet looking for a number. They say voltage controlled, so if we have a CV coming in here for plus minus 5 volts, we have a 1 to 3 ratio on it. And then there's an offset control that goes 0 to 12 volts. And then we have a pre-offset of 1 kilo ohm, 100 kilo ohm. Wait, what is that? Why is that marked down there like that? This is 100 and 150. 1 kilo. Oh, I see. 1K going into a 100 kilo ohm pot. The numbers are just in weird spots. Jesus Christ. I don't know what's going on here. Circles created with a V2164 circuit example in mind with constant change for modular synths. That said, I don't have much understanding of analog circuits. Welcome to the club. So I set the constants by trial and error, or in other words, by feeling my way around. So there may be some flaws. It works as long as it does. The circuit diagram above shows only one VCA to make it dual setup 2. Yeah, okay, thanks. There are 2 types of resistors that control the offset. The main is the 50 kilo ohm resistor on the panel and the 100 kilo ohm fixed resistor mounted on the board. The fixed resistor determines the rough offset, and the variable resistor controls it finally. The 150 kilo ohm resistor in the in part of the circuit is designed for modular synths that's used with 5 or 10 volts. If this 150 kilo ohm resistor is small, the output will be immediately clamped to plus minus 12. You can change the value of this 150 kilo ohm resistor to suit the instrument you are using. So maybe we do want to pull it back to be used with less than 5 volts. We might want this to work with 3 volts if that's the audio standard. Although Julian was saying that audio can be up to 10 volts. So I guess we want it to be full scale. Switching power supply, etc., etc., etc. Oh, that's a neat little board. Is that a plus minus 12 volt board? That's kind of nice. Could use one of those. Not a lot in terms of explanation of how to get the knob to control the input voltage to this thing properly. He has kind of like a biasing circuit here for control voltages that then doubles as a volume 0 to 12 volts in a 39 to 39. So is it full spread? Am I doing the full spread of the voltage? We found that not to be the case because we put a simple sine wave into the transconductance amplifier and we tried moving the knob back and forth. And this is these are 10K. Yeah, these are 10 kilo ohms. So, I mean, I guess there's a lot of current flowing on the 10 kilo ohms one. If we made it 50 or 100 kilo ohms, would that do it as well? That would give us whatever currents, it will give us whatever voltages from 0 to 12 on the outset. Let's, I guess maybe we need to set up that test again, but we need to make sure that our unit is in AB amplifier mode. So we need to put a 7.5 kilo ohm resistor on that. And then I guess we can plug both of them in at once as well. Get the other one over here and we can start setting that up. Oh my God, that only took us two and a half hours before we actually had a circuit. It's just the time scale multiplication of streaming is something that's just mystifying. It's kind of amazing. So the V2164, the pins that we're worried about, V minus is on pin 9. So let's get the pin 9s hooked up to V minus. Man, it got cold around here. It dropped like 20 degrees, 30 degrees in a night. What do we got? We got ground, negative 12, and then plus 12's right next to it. So ground and negative 12 are just to the right of the circuit. So pin 9 is actually over here, and pin 9 goes to V minus. No, 8, 9. Pin 9 is here, and that goes to V minus. All right. Our first mistake was trusting anyone. I need tweezers to kind of manipulate these things. That row's being very negative. You're right. You're right. You are right. You are correct. All right. Which ones do the... I think gray was the one that did it the best. It's green and gray. So that's minus voltage to pin 9. We'll get both of them hooked up like this. Of course, we're going to need the op amp on the output in order to observe things that are happening because I don't have a current sensing whatever. We can do it across a resistor too. You can sense the current along the resistor. But anyway, pin 9, pin 8 goes to ground. So that's over here. We can just do a jump right there. With my hand getting in the way because I put all the wires over on this side. So pin 8 to ground. Now technically there should be capacitors on these, 0.1 microfarad capacitors, which are designed to decouple the chip from the power supply. I've got a really nice Agilent power supply powering this thing, so it should be clean power, but that 0.1 is something that I'll want to put into the final design. I don't think it'll create tons of problems not having it right now. You know, in small scale testing like this, I don't think we really see any effect of that 0.1 off. Sometimes I could be proven wrong about that, but he's got 10 offs on it too. Pin 16 is positive power, and so that's actually right here, right there, because it goes negative 12, or ground negative 12, plus 12 ground. So a slightly longer, and I think red wire on this one. Pin 16 all the way over to this ground bar. There we go. Get this one hooked up. Dead hookup. And over to here. Yep, fought me a little bit. All right, both of the chips now have all of the different powers that they need. We now need a 7.5 kilo ohm resistor from pin 16 to pin 1. So we'll just put it up across the top there. 7.5 kilo ohms. Strange value, but the mode pin is controlled by current. It's not really so much of a digital thing. 7.5. Okay, well, let's see what we got. I did buy a decade box, by the way. I finally have a decade box. It's a little oh whoa-y. It's like a furry decade box. I don't know why it's so furry, this decade box, but I mean, it's a decade box. I guess it's a decade box. whatever, you know, I need a specific resistor. I can make it with this thing, with the jumpers. It's a little oh whoa-y though. All right, 7.5 kilo ohms. In some cases, if we get down to the nitty-gritty when we're doing this breadboarding, I could use my surface mount resistors just with a little adapter on it, and that would help me get exactly the value that I need for a resistor. Wait, that goes down to 22R. It goes all the way up to 75. 15, 10, 2R2. Well, these are like very disorganized. This bin has seen some better days. Oh, here we go. We're going down in value. All right, so 7.5, huh? 39, 8K2, 7K5. There we go. Wow, weird actually needing these and having them. I can't seem to stop using this tool. The fact that it is so expensive, I don't know. I guess it kind of justifies its cost in being so useful. But this little measuring tool that I have for breadboarding is just, for some reason, it's like the most useful tool. It's very strange that it's been so indispensable for the purposes of building these circuits. But it's plastic, and it breaks so easily. It breaks very easily because it's plastic. I have a little damage in this one where the one pinhole isn't quite as deep as it needs to be. But I don't know, for some reason it's just very useful. But it's so expensive. Kind of ridiculous. All right, so from pin 1 to pin 16. Try to get that in there, and then just like move it to the side a little bit. There we go. And that just sets our mode to an AB class amplifier, which has to do with how it's using transistors in order to amplify the output. I don't know everything about that. I know some are more powerful, some have problems with the zero crossing, and there's all kinds of different like hybrid ones. One pot is doing the linear logarithmic behavior of the input CV. So lin CD log to audio. Okay. I don't understand that fully, but yes, I think I get it a little. They still want $50 for this thing on Amazon. Jeez. Yeah, it's just because they have patents on it, I guess. And yet, I have yet to find a Thingiverse thing that does exactly the same stuff. They have other helpful things on the tool too. That'll help you bend leads and stuff. Like this stuff at the back end is all purposefully put in there to do certain tasks. What tasks specifically? I have no idea. I don't know specifically, but apparently this stuff will help you put together circuits too. Maybe it has to do with bending right angles. I think that's a booger, but yeah, something about all this stuff helps. Looks like there's cutting. Looks like stuff was cut there. The ruler I find to be completely useless, but you know, just this measurement and then this depth for the pin length. It comes with a free paste pocket protector. I think I don't remember where that went. I think I had that somewhere. Or it was in the same drawer that thing was in. All right, so we set up both of our amplifiers with power. It's got the mode pin set up for it as well. I do not know what to do about the control pin. I don't know what to do about the control pin and getting it to function within the limits of what we're doing. So we might as well hook up most of this circuit and just dive into it and see what it does. There's not a whole lot of extra electronics on this thing, according to our plan. We have mostly everything set up. So I'm gonna need a couple, and I guess we can only do 2 channels. So we'll do 2 channels from end to end, and that'll inform us of what the other channel should have on it. So we do a right and a left. I need 2 30 kilo ohm resistors, potentially a couple 50 kilo ohm resistors. I think, you know, that input filter might be better done on a perforated prototyping board if I just build that filter on the board with surface mount electronics. So let's get the board we made the other day. Where was it? Where did that go? Where did that end up? I don't think it's, it might be in here. Didn't it end up in here? Because we could just build that filter with surface mount stuff and then tap it into the rest of our circuit and figure out what's what. It's much easier for me to do because I have more surface mount electronics than True Hole. True Hole. My True Hole. Much easier. We got a bunch of, I have a history of making stuff like this. I've got all these helper circuits in this bin that I've made. So at least we can justify all of our effort the other day. Let's get this one. This will be a little bit big, but I think it'll do the job that we want it to. And maybe I'll put it over here. Maybe I just put it over there. All right, so for that, I'm gonna need a couple things. And it's gonna be 2 inputs, and it's gonna be just the input filtration stuff. All of this stuff. We don't need all this masked. Give me the rest of this. Dang it. Yep. All right. So what we're doing is we are going through a 30 kilo ohm resistor, and then we're going to have a 500 ohm and a 560 PF. Jeez. So much stuff that you guys are requiring of me. We won't do an input capacitor unlike the SS2164. I don't know why. We're just going to do whatever's in the documents in front of me. So 500 ohms. Do we have a 500 on this? Nope. On the next bin. Actually, I might get my resistor pack instead of these bins. These bins are 0805. That'll be fine. Let's see. Those are kilo ohms, but not 30 kilo ohm here. Why don't you guys come on back over here until we find our parts? So none of you. Yeah. This one. Capacitors. We have 560 pico. Should. No, our pico values, of course. Our pico values, or picofarad capacitors, jump in value because that's just as frustrating as it can get. So instead of 560 picofarads, we go from 120 to 1200 to 2700, just because of the way this thing is organized. Do I have a capacitor sample bin over there? Hold on. Looking over there. Diodes, resistors, capacitors. Maybe we have one in there. I just hate this part of finding parts. Finding farts, more like. You take that back. Capacitors is another one of these little sample books that I relabel because they're in Chinese. But we may have the appropriate value here. 560 pico. Where are we right now? 39 pico. 120, 160. These are incredibly useful. It's very satisfying to have a bookshelf full of these things. Of course, it also means you have a bunch of loose surface mount parts sitting below the the binders, because these are not the best things. They're not the best made things. 560 picofarad, believe it or not, is very often used. Well, not that often. Okay, I thought we were missing like a ton of them, because some of these values are often settled upon. So we're doing 2 channels of this, not all 4. So I'm just going to do 2 of these. 1, 2. And then our other things are the resistors. I should have the resistors in stock. Where's 560 go? 560 right here. And those will both go down to ground. So the 2 channels will be coming in. And I guess maybe I can have them share a ground. We'll just have them come in through one side and go out the other. And so if they share a ground, I can just use like this, this, and this to make our circuit. Maybe we should minimize. We'll go 1, 2, 3 from the bottom, just in case we have more circuits like this that need to be made. So the middle pin in this case will be ground. So I'm going to solder the middle pin. I don't know where those capacitors went. They're somewhere on the table. Oh, there they are. There they are in all of their splendor. You guys wait right there. This together, and we'll make that second pin our ground. And then we have, well, actually, no, we have 2 components. We have a 500 ohm that goes into the 560 PF. So what I'll do is, I guess, I'll do 500, 560, and then we'll make that a ground. So they'll both be, they both can't drop to the same one. They have to drop to separate ones. So that's actually not going to work. Let me see. So the resistor goes through here. That's 30K. And then I'll drop it to the 560, and then this one will be ground. Okay, we'll do it that way. Not going to be as efficient as I wanted it to be, and these are very small capacitors indeed. It'll at least be visually representative of the schematic. I'm going to make that work somehow. I need to make it a big bubble of solder. Very small capacitor. Tiny little guy. And soldering these 2 to the same pads is going to be kind of difficult. Because if I keep it in anchor mode, which is kind of how I have it right now, then they'll walk around when I solder on that spot. So I need to solder the opposite end of this one, and then that'll need to have a different resistor attached to it as well. I guess I just got to go full send on that. See, building circuits like this with surface mount stuff is what I love doing. That's how I like to operate. I'm going to get this out of the way before it gets ruined. I'm going to watch the plastic around the soldering iron too. Don't want to melt any plastic, make the funky smells. All the smells of electronics, you know? These are barely solderable on this board. Again, this is why I use the square proto board. Because the square proto board, everything's a little bit closer. All those traces are just a little bit closer to each other. And you have that back plane that's completely insulating. So you could tape your circuit to something. You'll be able to make 2 channels with this, and we'll be able to take a look at our differential output. So what I want to see when I solder this is that the solder flows up into the actual conducting portion of the capacitor. I want it to flow up into that as if it were liquid and coat everything, because that gives you that good electrical connection. So, I mean, 0805s, we can break out from the 0805s and look at 0603 resistors on this. So 603 I like to use for building actual circuit boards. The 0805s are easier to solder. That's just the size designation. It's the dimensions of the square in what is it called? Not mics, in mil spacing, which is just another way of having a slightly different unit to confuse everybody. Thanks for the pointers on the sizes. I really enjoy working with 0805. Yeah, smaller than that and it doesn't work. These are 0603, so these are the little brother of the 0805s. 0805 comfortable to work with. 1206, embarrassingly large. 0603, this is my bread and butter, but 0805s do prototyping a lot easier because they span those gaps in the perforated prototyping board. So here's 560 ohms, immediately found it. Oh no, we need 500, which is right here as well. Well, 510, I guess we'll go 510 instead of 500. 470 or 510? We'll go 510. We'll go 510. What could possibly go wrong? So 2 510s. 1, 2. I wish I could get bank for knowing all these things. If I could make a ton of money for knowing these things, have 10,000 subscribers and be a household name. That's not how the world works. So these are going from the capacitors into the audio channel input. So I'm going to take these and we will solder them up. Let's just put them over here for now. 0603 is getting down in size. It's to the point where it's going to be a little bit more difficult to solder things, but I can still function. It's basically the same size as the capacitor, though. So everything will look just about the same. We get this in here, and we put this right here. I don't think I would do very well with that many subscribers. If that were even possible, which it's not due to the nature of entertainment. But even if it were possible, like, chat would be moving way too quickly. It would be completely intimidating, the speed at which chat messages would fly by, and I would have to select which ones I read, and then I'd read all the wrong ones and get mad. Or people would get mad at me. Either way, it would be a disaster. Make sure that solder is definitely flowing all the way up to the top of the chip. And let's get the other one in there. 0402 is the smaller than this size, and it is impossible to work with. And I can work with it, and I have in the past, but you zoom in on the microscope, and all of the components look the same. They look like they're 0805 size because you zoomed in on them on the microscope. So you're like, oh, this is just the same. It's not. It's actually much more difficult to work with because everything's so tiny. And you feel inept just because of the size difference. What you're seeing with your eyeballs is normally sized circuits, and it's not behaving the way you want it to. All right, so now we need a 30 kilo ohm resistor. Oops, it's being grabbed by the pins by it. There we go. 30K. Well, that's down to the sample book again. 30K. 30, 200, 91. Okay, so we skipped a page. Yeah. 47, 30. There we go. 30K. And then I need to bring in the connecting wire and connect everything up. And then we'll have our input stage that we can then route to the output. And then the output we can hook up to the op amp, to a TL074. We'll have most of the correct components in there so that our voltage levels, I think, will be under control. Although I don't know, I still don't know how I'm hooking up those potentiometers. If they're just going to be plus minus 12 volts, we've already had that demonstrated to us as not working. So I don't know what our strategy is with that. I don't have any good ideas. I don't have any great ideas on how to hook that thing up. I guess we'll just be careful with the adjustment and just see what happens. That's sort of the experimental approach that we're taking today, is not really worrying too much about the numbers. Whether or not we need to do a 1 to 3 on the input of this thing. Since this chip is already made for modular synthesizers, you know, specifically made for modular synthesizers, so it should be compatible with them, as long as we can get whatever the headphone amp expects. And the headphone amp, I guess if we follow their numbers, we'll get the right stuff. whatever, what you call it, damplifying, whatever transfer function they expect, if we just follow that, we should probably get the same results. This isn't soldered on the top there. I think that's a problem that I've properly communicated. All right, so yeah, there. Now both sides of that one are in. Move on to the other one. This is very small circuits, and the reason we're doing it like this, not to save room, just because I have more of these components. I'm able to build this filter using these components, and I've actually built it wrong. I've built it wrong. We're going to flip it over. The inputs are on the left. The outputs are on the right. That's fine. It's fine. Everything's fine. We're fine here. I'm not losing my mind. I'm losing my mind. Yeah, because the input actually goes through the 30K first, and then the filter section. But it's symmetrical, so I can just flip this over. I don't think that's fully soldered. Let me try that again. Whoa. Too much heat in the area. Everybody's moving around. There we go. Perfect in every way. Let's give it a ground. And to do that, I got rid of all that wire. Damn it. I gotta cut a new piece. We'll just use a jacketed wire and I'll cut it. I have way more of the jacketed than I have the unjacketed. And so I'm trying to like even out my wire usage. When I build a circuit like this, I'm not using the jacketed wire. So the unjacketed gets neglected. So here I can just make unjacketed wire by pulling the jacket off. By jacking it off. Jack in the box. And then cut it. We'll use the knife to cut this. I could do metal fatigue, but I could also just put a blade right on top of it and then do that. So pick your poison. You can either sit there and go metal fatigue, metal fatigue, metal fatigue until it breaks off, or you can do the blade method, which is quiet. Just for fun, we'll just do a full ground bar. Oh, this iron's stinky because apparently I picked up some fabric somewhere on it. Whatever that stuff is on the end there is very, very stinky indeed. All right, there we go. Get that off of my iron. Ugh. The iron is very hot, 666 degrees Fahrenheit. And so it will burn stuff and it will make plastic stuff smell. So if a stray dog hair finds its way to the iron, and they do, then you will smell burning dog hair. It's awful. It's terrible. It's just the worst. I mean, I think I have seen, no, well, no, nobody's ever done. Don't put the iron to your mouth, like, under any circumstance, because there's some truly awful shit that gets onto a soldering iron. Truly terrible carbon stuff. Very bad for you. This is not working out. Ow! What the? I'm completing some kind of a circuit with my power supply. Oh, I hate it when that happens. So what was happening is I'm holding a little piece of wire, right? I'm holding a little piece of wire to here. And then the back of my thumb connects to this wire right here, which has a ground loop all the way back to the positive of the power supply that's off. And when I touch my iron to this, I'm putting a ground potential from the electrical outlet onto that line, and it's feeding through the wire, through my thumb, and it's causing my palm to buzz a little bit. That was crazy. Like, why am I getting that? Am I getting electrocuted by my very simple electronics here? Also, why isn't this melting? What in the world? I have to add solder to this because it's like fighting me. the oils from my skin, I think I got on the wire and called up their friend. No, the oils from my skin got on the wire, and then that keeps the solder from sticking. And since I haven't added new solder there, there's not a lot of flux to go around, in spite of it being rosin core. Okay, last one. And then we have our functional input circuitry. We won't have output on a jack. I've got the two Thonky Kongs on a little board. Those will be our inputs that we will mix. I don't know what inputs I have. I don't have enough inputs to mix, but we'll at least be able to take the channels all the way out to fruition. See what happens with them. Okay, so that's our input right there. Look at it go. Let me just touch up that solder on the one pin there. And carefully, because the wire is actually going to carry all the heat, and both of these will become molten simultaneously, that means that when I pull my iron away, it might take the wire with it. Since surface tension in metal is pretty strong. That didn't work at all. Give me this back. Put that in the dry sponge. We'll flip the iron over. Maybe that'll have slightly better contact on this side. Nope, it keeps stealing it. Come on. There we go. Jeez, this is not very exacting. This is very sloppy soldering. All right, that should be all right. It's not pretty, but it'll get the job done. All right, so now we can get the solder out of the way. Flip this over. And that is our input filter. A little space to do other stuff if we need to, but we'll route the input from the two jacks through that. So actually, we'll turn the script over. Let's put this down here and put this over here where it's closer to our inputs, which will be down here. I mean, I could move this anywhere too. It's better to just move those for now. Those can go a larger distance. I want these to be kind of short. And we're coming in down here, and then we're going to have a big section of nothing. So I'll put these facing the other way. Haha. So our input will go, yoop, just like that. Beautiful. Okay, so let's take a look at this. Let's see. So over here we have our connections. So it's going to be ground, two ground connections actually, because one of them is the output pin, but then the other one is the disconnect pin. And I think I want the disconnect pin to go to ground when it's not connected. So we're going to connect all three of these: ground, ground, output. So I'm going to need connections to ground, which are the slightly longer pins. Means sample book is not necessary anymore. And I need to find yumpers. Here's some yumpers. This is the disorganized one. Let's find, well, the better kit. I don't know where the better kit is. It's somewhere around the corner. Let's just close up the resistor bin. I'm probably going to need to do 30K feedback resistors for the output op amps. That's going to get a little bit more messy. I'm going to need more surface mount parts for that. We'll have to do a little female pin header that fits onto the board. All right, so ground on the ground pin. Let me unplug this just so we have room to work. So on the ground pin, go ground. That's -12. Wait a minute. Ground is the upper pin, so I need yellow, the hard to find jumpers, the ones that are more in demand. That goes, oh, am I going to yeah, I'll have it on both sections. I don't know why they split up the holes on these things. Split them up and they make them hard to like get to. You have like that little space in your vertical ones. And I think some manufacturers have like taken it upon themselves to make theirs be the special one that doesn't have the gaps. But it's like you never buy those. You never end up with those. You always end up with the cheap ones. And the cheap ones have the little gap in the holes, signifying nothing. I don't know why they would do it. It used to be that the gap would signify that they're not connected together. and then you would have to run jumpers in the mid plane of your board, just right in the middle of your bus lines. I have these little jumpers. That just sent to space. It just went to space. Oh, and that was a precious one too. That was one of the precious few yellows that I have. I got some more. Maybe we can make this work. We've been doing a lot of these analog circuits, and so the analog circuits are using a particular type of jumper, and I like to keep the circuits together until I'm done building the thing, but I may have to take apart our module testing module board in order to get jumpers back, because they're in short supply. I could just spend $15 and get another kit of jumpers. I could do that. I could just buy another kit. It was $14 for 3 kits, so they're not exactly breaking the bank. Oh, and just to double check what pin is what on the Donkey Kong, I had a loose Donkey Kong. Where did it go? Where is he? Where do you go? Donkey Kong? Where have you been? I think it ended up, yeah, here it is. So just to check, the pin goes all the way in and it offsets. So this is the disconnect. No, this one's the disconnect. This one's our output signal. Kids or kits? I don't know how much kids are these days. I haven't looked up the prices. No, kits, wiring kits. Wiring kids, I think we did away with those laws, but they're coming back. So sooner or later, we'll be able to send the kids back into the factory. They're working on that. They're passing some laws, which is really cool. It's really cool because kids have smaller hands, and they could really get those smaller hands into the machinery. And they've got a lot of free time. What are they doing with their time? Not working. So it's good that we've finally gotten to that. All right, so what length jumper am I going to need in order to get my input signals into my input filters? Well, unfortunately, it is a longer than yellow, and yellow is that wonderful size gap where suddenly the jumpers become mega super long from just being average length. So it's like when you get to this size, you're SOL for finding any longer jumpers. Orange looks like it is longer, but I don't think it's going to span the gap that I need to go from here. Oh, you son of a bitch. It's 1 pin off, and it's like, this would be super clean if I could get just a slightly longer jumper. Red? Is red gonna do it? Red's gonna do it. Okay, red is our savior for this one. For the other one, I don't know what's gonna happen. I'm unsure. Save us, red. All right, that's one of them. And then this one needs to go down to here. And I don't know what length that's going to be. Let's see if orange will do it. Orange. Orang. Help us. Oh, orange is perfect. Oh, nice and clean. So there's our 2 channels going in there. I need a ground here. And fortunately, I chose exactly the right spot. Damn it. It sucks. Come on. I'll use a green jumper. Oh, wait, no, it's the shorter one. So I think I can still use a yellow jumper, but I'll go in sort of sloppy fashion. Just go like this. Come on. There we go. Just like that. Okay, so now that's connected to ground, and so there's our filter. And now these are going into our first set of V2164 inputs. I don't have tons of inputs that I can throw at stuff. So we're only testing 1/2 of the circuit because we've only got these 2 right here. But yeah, okay. All right, so the inputs are on pins 2, 7. Those aren't looking very good. 2, 7, 11, and 14. So 11 and 14 are inputs, so we might as well just use those. So 11 and 14 have to go to here and here. Well, boy, that's rather convenient. I didn't plan for this. This is just a happy accident. Look at this happy accident. What the hell? These pins are lining up. They're lining up perfectly. That's crazy. This is some crazy shit here, man. I didn't plan that out. I didn't plan that out. My ancestors smile upon me. Oh, we need a longer jumper than that, though. I think they might need reds, which I don't know if I can find more reds. But yellow's not going to do it. Orange? No, they definitely need reds. So I need to find another kit, or I need to find reds in this one. Oh, here's some reds. 1 red. 2 red. The alternative to doing this is to find the kit with the white wires in it that are super duper long, or the ones with, or use green wires, and then the green wires are super long. They're like, yeah, they're huge. So those would have to be like squiggled on the board in order to fit in. I like things to be flat and neat. I like flat and I like neat. So this one goes into pin 11, which is actually this one. Right? 16, 15, 14, 13, 12, 11. Yeah. That's confusing. That offset there, they really should bump that up a little bit. I don't know what they were thinking when they printed this thing. Because that is genuinely a little bit confusing, and a little bit confusing is often enough confusing to cause danger. So yeah, there we go. Okay, so those are the inputs from 11 and 14, correct? And then the control pins for 11 and 14. Oh, 11 and 14 are the control pins. It's 10 and 15. Well, isn't that convenient? 10 and 15. I would have been going into the wrong pins. Would you imagine my embarrassment? Just completely. Come on. Why is it stuck? Jeez. Trying to come out at an angle. Unfortunately, breadboards can get old. They can become aged, and they can become less effective with their little pincers not pinching down on the metal. And that causes all kinds of issues when it comes to troubleshooting. It can get very, very frustrating if you build your new, modern, amazing circuit on a somewhat aged breadboard. Okay, so as far as things go, we've connected everything, and now we've got our outputs, which are on pins 12 and 13. We're moving further in. Our outputs are on 12 and 13. Our control pins are 14 and 11. But 12 and 13 are our outputs, and those are going to another pair of amplifiers. And since we're only building half of this circuit, we don't need to hook this one up. We can just unhook this thing, this driver, because we're not doing the full circuit yet. We don't know all of our values yet. So we'll just leave this one hanging. I'll put that into the ready room over there, and we'll move our op amp a little closer that we're going to need on the output. That's convenient. And what we'll do down here is we're going to double up the drivers. We're going to double them up, because apparently that gives us a ton of gain or something. It gives us something. It said, somewhere in the data sheet, it said, double driver better, real good, go for it. And I said, okay, you don't have to say anything else to me. So pins, what? 4 and 5 are going to be connected to one another. Pin 4 and 5. And so I can get one of these little metal jumpers, the seldom used row-to-row jump. If I could find one. I mean, I've got this one, but this goes over one pin. That goes over top of a pin. We need to go right from pin to pin. Pin to pin to pin to pin. Pin to pin. Let me grab one of these. There it is. These are easy to miss on the board, too. You got to be careful when you're using these things, because you'll end up biting yourself. You can be like, oh, I didn't know those 2 pins were connected together. Put it right here. Put her there. Because this will be taking a slightly longer jump over to op amp land. That's the output, pins 4 and 5. And then pin 2 and 7 are also connected. This is going to be like playing chopsticks on a piano, where we have to connect these things like this. Pin, what is the 2 and 7? Yeah, that's okay, slightly shorter than that. What's shorter than that one? Not that one. Maybe this one's stretched just a little bit. Actually, doing the 3 of these like this, I think maybe I'm better off just doing it like down to the side, because there's not going to be room for all the jumpers. Yeah, I'm gonna use longer wires for this, I guess, and just bend them. How much longer is longer? Seven. We'll go this way, and then we'll go. Oh no, that's gonna look like shit. It needed to be a longer wire. If only it was a longer wire. That's fine. 7 and 2, and then the control pins, which are 6 and 3. That's this to this. So you can use another yellow wire, maybe get away with it, or a white wire. Let's do a wet wire. Bend that in a particular fashion in order to create a U shape. That one would actually work on this one. Be a slightly smaller version of it. Hold on, I'm getting there. I'm getting there. You guys just be patient. Two and 7. Maybe I'll just go straight across to 6 and 3. No, it needs to be shorter than green. Gray, maybe. Maybe gray. Shorter than that. Okay. What is shorter than that? Well, it needs to skip over 2 pins, so the black one is not going to work there. It's going to be one of my precious yellows, isn't it? My precious yellows. The yellows are very precious for doing power hookups and stuff. Sorry, I got more kits. Ah, where'd it go? Sorry. How did it get that far? Very big leap for that thing to take. Okay, so there. So those are hooked up in parallel, which apparently we can do. Pin 1 has got its mode signal coming into it, AB mode. And then the output of this goes into the op amp. And so I go over here to where the op amp is on the schematic. Yellow is 4 on the resistor color code. Oh, interesting. That's kind of neat. And so we then go to 2 op amps on the output. So the TL074, I guess I could mark down the pins if I really feel like it, but it's basically the center here is positive and negative 12 volts. So we have, and then you have 4 op amps whose outputs are facing away from the power input. That's sort of the standard scheme of pins on the where is that? On the op amp. Did I close the op amp datasheet? No, I kept it up. So you have your outs on the 4 ends, and then your in plus and minus heading back to VCC, and in minus is closer to out because you typically will have your feedback between these 2 pins. Let's see. I have to hook this thing up 4 ways to Sunday, and I need it to look like this. No, and I need it to look like this. No, and I need it to look like this. So the pluses and the minuses are opposites, and then, oh yeah, where is power und ground? So VCC plus is on the pin 1 row. Let's get this hooked up to power. So VCC plus is on the pin 1 row, which means I want to flip this 180 degrees. Yoink. And we'll leave a little bit of room between our devices. So VCC plus is over here. Oh, I got it just in the right thing. Plus there, minus over here. That's going to be a green. Lucky for us, this circuit is rather simple. I'm going to be able to get this together, and we'll be able to take a look at the output very quickly today. We spent a lot of time coming up with what the circuit should look like and trying to get it as simple as possible. The only thing that I'm sort of unaware of what exactly I'm supposed to do is how to get the potentiometers to actually control it. I don't know how to do that. So yeah, let's go. So we've got 2 amps on this side, and we've got our 2 outputs coming from pins 4 and 5. So, or rather, 1 output coming from 4 and 5. And we're going to go, that 1 output is going to go to 2 op amps. Green is 5. Were they following Roy G. Bidd's colossal circuit guide to numbering? All right, so our plus and our minus are going to be interconnected with one another, because one is going to be on the plus side, one's going to be on the minus side. We're going to have an inverting and a non-inverting. And then we need to somehow conjure up, I guess, as close to a 30 kilo ohm resistor as we can get. And it'll probably have to be a physical resistor. And it'll be between minus and plus in output. So that's going to also vary. So its pluses are closer to power. So if we take that one there, then we're going to need a jumper that goes a little bit further, which will be something like orange, I guess. And that'll go into minus all the way up here. So then the output, it's going to be kind of tough to hook all that stuff up, but we'll figure it out. Let's see, we have from here, oh, that's going to be annoying, here to here. It's probably going to be another black wire, I would assume. I mean, I could always move the black wire over, but things are kind of neat right now, so I'm going to keep it neat. Okay, there's that. What we don't have hooked up right now is the control. We'll figure that out in a minute. I guess I'll put it to the 2 knobs over here, and they'll just be super sensitive. The knobs all the way over here. They'll just be super sensitive like the other ones were on the other setup. So there, and we're hooking up to those, and then the outputs are going to be here and here, and we're going to observe those on the scope. So now we need a 30 kilo ohm resistor to go in between as our feedback resistor. Or actually, no, it's not a feedback resistor. What is it? It's a transconductance something or other. Current feedback. But it turns it back into voltages. So I guess that's just our output impedance. It's weird though, because that amplifier, I guess the amplifier we're getting uses voltages. Yeah, that's okay. How did they do theirs? They have like 1 kilo ohms to ground in their circuit, the one for the audio thing. But I guess their driver, their DAC, is not putting in the same voltages as with modular synthesizers. So where is that? It's somewhere around here. There's just so much referencing when it comes to building something like this. You know, you're looking at other people's designs, you're looking at your own ideas of what the design should look like, and more so than anything else, you're looking at the designs that are in the data sheets, what they suggest you do. And so what they have here is they have the transconductance amplification going on. They put it into a 1 kilo ohm, and they've got a 1 kilo ohm to ground on the plus end going into their device. I don't know what that means. I don't know what that means. And so we're not doing it on ours. We've got similar stuff going on, but all right, well, let's get as close to 30 as we can. We'll get those hooked up. So 30K, 75K, 47, 39, and then it makes a big jump. And that big jump is jumping over 33. Okay, 33 will do, although I'm running out of them. 33 will do, and since these are going on amplifiers, I can make them minimum 33 resistors, which means just bending the tip of the thing down with the other one. What does that mean, Bother? What the hell did you just say? It doesn't sound like language. All right, take the tip, take one of them, just bend them down. Bend it down like that, and then we cut down here somewhere to make the leads even. Now that means that this resistor can now go across from the output to minus, just like that. And then the other one can go from the output to plus just by having it span a slightly larger gap. So output down here, and then plus is right there. Do that. And those are minimal resistors, although, you know, the amount of contact is going to be annoying. The thin lead resistors is unfortunately a necessary evil, given the price of everything. Everything's cheap, and so these save on metal by having smaller leads. So the opposite end of the input goes to ground. It's being compared against input. One is comparing it positively, the other is comparing it to the negative lead. And so, oh, I guess just again, the coveted yellow jumpers, which I don't know if I have a lot of. Seem to be running out of them pretty quickly. I keep finding them though. In spite of like steadily running out of them, I keep finding them everywhere. Oh, come on. Why do you do this to me? You know, sometimes I really hate solderless breadboard. Sure, we can put the circuit together fairly quickly, but it fights you in every dimension. It's like, there, jeez. You know, everything's getting cheaper, and these are no exception. So the cheapness of these is starting to really kind of hamper my ease of use. They've never been particularly expensively made, though. They weren't exactly, you know, carving these things out of brass. They've always been inherently super duper cheap. So, I don't know. So this one right here, I need to connect to ground. I need to find a yellow jumper, and I think I have finally run out of yellow jumpers in this kit. And I just said that, which means, oh, I just found one. It's like a law of the universe. Fairly interesting. So this one to ground with the final yellow jumper. It's possible that there's one more, but I started to have to really look to find this one. And then it doesn't plug in because it's all the... God! So mad. I'm so mad. Oh, and then it plugs in with no effort at all. Yep, you got to get it aligned just right. Okay, so that concludes hooking up the amplifier. We don't have the capacitors. I just don't have that value of capacitor to put in. Maybe I do surface mount, but I'm not going to make something. I'm not going to build something because it'll be clunky, whatever we build. And the capacitor is going to have sort of pretty minimal interaction with the rest of this thing. The only other part that I could think of would be to connect the two 10K ohm resistors to their control circuits, even though we know it's going to be kind of wonky control as it was before. But we have two circuits here. So one of them is going to be here. Oh, and we need to wire the other ones up together. Wait, what did I miss over here? We didn't hook... Oh, yeah, I need to hook the two channels up to one, the two outputs of this thing. So we'll hook them down here, and then I'll sneak over to the inputs over there. So I still have stuff to do. We still have so much to do. So let's see. We're taking outs 4 and 5, which are fed from inputs 2 and 7. And they're hooked up to the same thing because we're doubling it up because they said I could. So 7 over here. And that goes to pin, well, hold on, 12 and 13. So actually 12 and 13 get connected together. So we get another one of our little jumpers. Our little huggies. Get a little huggy over here. Get that little huggy. Just drop it down like this. I'll drop it down over here. That'll be the best place for it. 12 and 13, and then the output is coming from pins 14 and 11. So this will be the next jumper, which is a fairly small one, and it's probably the size that I don't have, huh? Yeah, because we did it with the yellow jumper. Oh man, I gotta find one more. I just don't think there is one left in here. I could maybe crush a green onto it. Maybe. Come on, universe. Deliver me one more yellow jumper. It's impossible. It's impossible. It doesn't exist. It doesn't exist. I'm going to have to defile the mixer design. Not the mixer design, the module tester design. It's got to happen. It's got to happen. Everything's temporary. Nothing is forever. There's like tons of yellow jumpers on this thing too. It's a very special four pin jump that's like so very important. Actually, let's move this up. And then this goes across here. All right, and then this is our output. This is our control, right? No, this is our output. This is our control. So this is output. This goes to here. That's a fairly big jump. I guess I'm going to do it with a green. I'll use a green for this. Actually, green's way too long. Can we get a little shorter than that? No, no, we can't. We can't. Nope. Nope. Red is the shorter one, and that's going to be way too long for this jump. Or it's going to be way too short for this jump. Although I could pull up the adapter and just do it from here to there underneath, but that's not good circuit communication. You kind of want at a glance to know what's going on in your circuit. So I guess we're going to use a green. It's going to be way too long. There was a kit I had that had white wires that were the appropriate distance. So 12 and 13 are the outputs. We go all the way up here, plug in, and we go all the way down and around. It's a huge circuitous route. Oh my God. Supposedly it'll be less noisy because it'll be conductance instead of actually voltages, though. I don't know why that is, but I guess that is. All right, so there's our little... God, that is so terrible. It's so bad, but I don't have any, like, slightly the right length things. It just doesn't work like that. Blue? Is this blue longer? It's not long enough. I bet you in the dregs bin I have something that's correct. I don't know where the dregs bin went. Oh, it's over here on the other side. Hold on. Let's take a look. Hello, I need help on my circuit that isn't working. How do you analyze your circuits? Yeah, I mean, you can use a multimeter, you can use an oscilloscope. There's a couple different methods that are effective at analyzing circuits. The biggest circuit analysis tool that you have is logic. And I know it's kitschy and you want, like, you should buy a piece of equipment. I do not know what pieces of equipment exist that will help in circuit analysis for the beginner, because all of my tools are for the advanced circuit analyster. It's hard for me to suggest what, you know, beginners should really worry about, because I'm beyond that. I have these tools that are like expensive and amazing at doing their job, like the oscilloscope over there. There are handheld oscilloscopes and smaller electronics that you can buy that will allow you to do all kinds of circuit analysis. And depending on what your application is, you may not need a full oscilloscope. You might just need a multimeter. But I don't really know that. And I don't know what you're doing. And it's hard to suggest things. It's a very difficult question, actually. But I think if you root around and you do a little bit of research, you can kind of clear up some of these questions. You come up with something that'll work for you. Because like a multimeter is really good at figuring out what the thing is, sitting there stationary in the circuit. I just don't have the length. I just don't have it. Common problem, not uncommon for men. But, all right, I'm going to jump them down to the bottom there. We'll go from there. I can't believe I don't have the right length wire. There's like this middle length of wire that just isn't included in any of these kits. And you just got to work around it. It's too close. Let's get a little further away. Using the gray wire all the way down to here. When we analyze this, part of the circuit is going to be in conducting mode in amps mode instead of in voltage mode, which is very confusing. This thing is just not cooperating. This is, of course, where one of the viewers comes in and says, this is why I cut all of my own wires. And I go, I don't know what that is. I don't know what that is. I don't do that. I don't cut my own wires. Ah, going across there is gonna, it means another yellow one, or I can take a green and just go a little bit wider. And then we got to go this distance. So that's going to be probably this. Yeah, maybe this. Maybe it's blue. It's rather more jumps than I would like. It means that it's got susceptibility to noise and other wonky circuit stuff that might happen along the way, but you know, this just keeps it down against the board. Good enough. There. So our inputs are coming in here. We have a control signal that's shared that will get connected up to our first potentiometer. I'm looking for a wire for that. We could do a red wire. Red's way too long. And I'm missing all my greens. What's going on here? Here's that fabled white wire. We can hook up there. And so that's going to go to our first control here. Oh, it's too short. Son of a bitch. Okay. A blue wire is going to be way overkill. I think if I can fish a green out of here, it'll be just right. There's a green wire. Go to our overly sensitive 10K ohm controls. A little bit long for that. And then we need to hook this up to plus and minus. And so minus 12 is here, plus 12 is here. Because I thought of these in, it's basically plus 12 ground, ground minus 12. So we can do plus and minus just by going here and here. So minus 12. One side of the pot. Ah, of course, it's been longer than that. How did I do it with the other jumpers? Maybe it was this one. Let's see, that one is, oh no, that's minus 12. Yeah, okay, so that'll get us to minus 12. Minus 12. We'll do the same thing with the other one, I guess. That goes to here. Come on. One thing that keeps these from plugging in is when you come in at an angle. The jaws don't like that. Okay, so like that, and then the other one goes to the one right next to it, which is going to be what size of jumper? Shorter than blue. Which one of y'all is shorter than blue? Green. It's gonna be green. These are always similar colors to do all these jobs on these boards. All the different connections. I should find a spool of solid core jacketed wire that I could use to make my own jumpers, because that would be kind of nice to not have to fish around in these wire bins. It's like finding just the right Lego to do some kind of thing. There was one time when I was a little kid, and I guess my dad probably got yelled at for not spending any time with his kids ever. And so he came into my room. He said, I want to help you build with Lego. I was building something out of Lego. I don't remember what the hell it was. I think it was a little biplane or something. But I was running off of a book, and our bin's full of Legos, deep bin full of all the Lego stuff that we had taken apart. And I said, I'm looking for this piece. And so my dad ended up digging around for like 20 minutes. And he finally found exactly that piece. And I said, oh, I'm not worried about what color it is. I didn't care about what color the Lego piece was. He found exactly the piece in exactly the color that I was looking for. Oh, he must have been like, all right, kid, have fun, and just like left. All right, so this is going to go like on top of everything. This is an unfortunate run. So maybe I'll bend it a little bit like that. And then we go to the control pin, which is pins 3 and 6. That's this one here. And that, my friends, should be an amplifier. Try to like make that run make a little bit more sense. That's a little bit weird. All right, so referencing on ground, which we already have hooked up, and going to our outputs, which should be voltage on the two ends of this guy, we should be able to see a differential signal that resembles our input. So I'm going to get one more channel on the scope. It's up here. One more channel on the scope. This one's white. I don't think I have a white channel. Well, it's going to be channel 3. I always love it when we get to fully utilize the scope like this. Channel 3. Let's enable channel 3. Channel 3 is the dark, whatever, fuchsia? I don't know, what color is that? And then we'll hook that one to the other end of the differential. It'll be on the other op-amp output here. So now we have 2 channels hooked up. I can turn this on, get our input going. We've got to clear a little bit of space off so I can get to the power supply. Oh, if this works, I'm going to be happy, because that'll be a nice, that'll bottle up the episode nicely. I'll have a nice beginning, middle, end, and we'll have a plot that goes from idea to circuit to function. Of course, the knobs are going to be a little bit weird. The adjustment's going to be strange. And in order to hook up this power, I'm going to first unhook the power, because in the infinite wisdom of Agilent, they decided that if you were to hook up a power supply and get it to output particular voltages, you would love nothing more than to output that power while you adjust. So they put the text output off on their VFD display. This is a like mid-90s power supply. It's pretty cool. I like it a lot. It makes very clean power. It's a professional power supply. But it doesn't, you have to turn it on in order to output voltages. So I'm going to take my plus 20 and take it up to 12. Then I'm going to take my minus 20 and take it up to 12. There we go. And that's our input power for the rest of the circuit. Now, I'm going to turn output off. So it's all on one button. Move some of these bins out of the way so I can actually get to things in case I need to turn it off suddenly. And then put the 2 similar leads on the plus and ground. So the red and the black that look the same go on plus and ground, and then our special guest, minus 12 volts, goes on the other type of lead. It goes on the big alligator lead, and that's these 3 right here. Those go to jumpers that go to the rails, and the rails are all connected together. So now I should be able to turn on power, and we will be able to look at our frequency sweeping through the device. And so that means we should see 2 waves on the output, 2 opposing waves. And I should be able to have volume control over those 2 waves. If I had any moderators here, if they weren't fast asleep and or streaming themselves, we could put up a bet about whether or not we think this thing is actually going to work. Just in case everything explodes, I want to get things on camera here. Try to do this. That, like that. This in this area. Oh, and of course it drops out because these BNCs are not the best at connecting stuff. So we got the OO resistor decade box. All right, you guys ready? And we're gonna look. We're looking here. We're looking for heat. You can see heat being generated over by the frequency generator, but over here we're looking to see if anything heats up too much. Okay. I'm not seeing a huge draw on 12 volts, although there is a little bit of draw on 12 volts. This thing gets toasty by nature. And if I try to adjust, almost had something there. I have 2 adjustments to contest with to try to get output on this. All right. Oh, it smells like burning. No, it's not that hot. It certainly smells that hot, but it's not that hot. All right, so what's going wrong here? The real way that I can test the input. Oh, I'm not inputting. Oh, I see. It helps when you actually give the channels the thing. So let's try to get these both into a good adjustment area where it's not bottoming out our circuit. It really shouldn't be bottomed out. It should be on 0. Yet for some reason, my differential voltages are in a weird way. They're in weird spots. These are things that we're going to have to resolve in the circuit. Let's give it an input. Cool. Cool. Okay, cool. Yeah, nothing. Oh, this failed. Hey, come back. Come on, B and C. There we go. Stupid thing. All right. Where's that? That's a weird jump. That's, oh, I almost got something. I have to balance 2 stages of amplifiers in order to get an output. And these things are rather sensitive to a particular voltage range from negative, I think, 300 millivolts to like 3 volts. I really should tune them with some resistors. Be nice if I could actually see some opposing outputs from these two. I think they're all in the same range. They should be anyway. And then the other question is, should the ground pins be floated? It doesn't look like it's doing anything, though. Because that's 2 channels mixing. It goes into there. So our original signal's not coming back out, is it? I mean, I see like an inkling of it on one of the op amps, but the other one is not really displaying it much. That one's there, this one's here. So let's drop in on another part of the circuit. Let's see what it looks like here. Nothing. Okay. But over here, nothing. Nothing. Voltage level from the potentiometer. So let's keep that sort of not very well connected. All right, let's do like somewhere approaching 3v3. Like we'll put it like right there. And then the other one, which is the second stage, will be somewhere approaching. Wait, did I just adjust the wrong one? I did. I adjusted the wrong one. Damn it. All right, hold on. Right over here. Did I get my ins and outs mixed up? No, it's pin. Yeah, 12 and 13 are the output. Okay. All right, so I'm going to take that to like here. And then this one, bring it to like right there. And then we've got the 2 differentials here, not really expressing themselves. The singular output from these amps is not really going to be that visible to our thing because it's going to be in current mode. Yeah, we need the op amp on the output in order to translate it over. But by all means, this should work. Because we've got current mode output going into current mode input. So that shouldn't be controversial. One of the op amps might work better than the other one, but it should still function properly. We should still get an output signal of appropriate amplitude out of this thing. So something's a little funky. What is our signal? What does our signal look like when it comes in? Okay, that's abnormal. Why is it clipping? Well, how would you be clipping? Why would you be clipping? Oh, and there's just nothing there because we're not plugged into that one. We're plugged in here, but it's clipping. Why is it? What in the world is going on? Pin 15. What's that thing? Really shouldn't be. At this is an audio voltage level. We've got it at 4-volt peak to peak, I believe. Amplitude 5-volt peak to peak. So this would be a full like control signal coming in. And it's for some reason after the filter, after the 30 kilo ohm filter, it's breaking down, and it's got the same capacitor and everything. That's connected to ground, right? Yeah, it's connected to ground. Ground. Everybody's connected to ground. So they're all connected to ground. Is it the right direction? Yeah, it hits the 30 kilo ohm first. Where is that? We come down all the way here, and we go through 30K, and then we have the 500 some odd ohm to the capacitor to ground. And this is ground. Huh. So what's going on? What's the problem? What seems to be the problem, officer? After our filter, it's cutting off in a weird way. You can see it just in there. So what if our amplitude is 4 volts peak to peak? Or rather, if we go 3 volts. How do I escape? 3-volt peak to peak. 3 volts is what my friends called too quiet. That was the M303 was putting out 3 volts. What I don't understand is what's affecting our audio path already. That's strange. But all right, all that aside, this is the very beginnings of the input. The very beginning of the input there, that gets output here. There, it gets output here. Of course, we can't see it because it's current. It's not a voltage. So we just see this weird pattern. So as I adjust that, that's just affecting the weirdo pattern that we see on our output. But if we're getting that weird pattern there, we might get a full wave out here. Or no, that's not how that works. Over there, we get weirdness. Wait, where's the other signal then? Oh, it's on a different scale, I see. What are our scales here? Channel 1. Okay, 246. Channel 2 can be manipulated a little bit there. Put that there. 246. Channel 3. 246. So they're all on the same scale now. This one is heavily negative. Highly, highly negative. Why are you so negative? Cheer up. Those are both referencing ground. They're definitely referencing ground. That goes to ground. That goes to 12 volts. One I have in a positive and the other I have in a negative. The one in the positive mode, or sorry, the one in the inverting mode should still work, and it should still just invert the output as a voltage level. Do I need additional electronics? They didn't show any additional electronics on their data sheet. I mean, they literally just had 30K and a 100 PF, and we've got close to 30K. I think it's 32 or something on that section right there. So we should just see voltage output. And then if I do the inversion right and I reference it off of the opposite, then it should do the inverted voltage output. And since we're both going through an op amp, there should be very little phase delay, which is what we could have looked at if we actually got an output from this thing. Hey, what's up, Silly Russell? We're hooking up amps in all kinds of weird, funky ways to try to make a mixer, but as usual, things just kind of didn't go right. Things just kind of went a little funky. He's got a little funked up. Celia Russell has gifted a sub to Lev TV Live. That's 111. Holy crap. Celia Russell, thank you so much. Thank you, thank you, thank you. Can't get enough of it. Appreciate you. Yeah, we're trying. I mean, we're trying. I don't know. This is a very simple circuit, so not a whole lot to go wrong here. Those two outputs go to this that has outputs. Control signals coming in there. control signal goes to the other control signal through there. This is the input. This is the input out here, input out here, control signal here, output is shared, output comes down and around. This is two separate outputs. Then we combine them over here just to show off that this chip can do that. And then we go from out here, we go to a bus line that takes us to the negative feedback, the negative, the inverting amplifier, and a non-inverting amplifier. Both of them are hooked to ground. So the plus and the minus are both hooked to ground. The overall circuit is connected to ground as well, connected to positive over here. These are floating amplifiers. I don't think they're too much of a problem. Very simple circuit, not a lot going on here. It should work, but it doesn't. 84 of my gift subs have been to Leb. That's funny. You don't have to maintain Leb's status. I know you want to, but you don't gotta do it. It's okay. I appreciate that you do it, though. So, like, I'm seeing dropout when I adjust stuff on the one end. I'm not really seeing any clarity in the signal. It sort of does what this thing does when it's in current mode. So does that mean that I need resistors to ground like they have in the other circuits? Problems in a simple circuit are the worst. It just feels bad when there's so little going on and it doesn't work as expected. We had the thing working yesterday too, that's the thing. We had a single one of these sort of transconductance amplifiers sitting on the output of just one channel, and it worked just fine. We overcomplicated things in trying to keep it simple. We added a bunch of cross connections, and we're using some of these things in parallel just for fun. And by all means, it should work just the same, but for some reason it's not. Because we need differential output from the whole thing to go into the headphone amplifier. I don't have to, but it's like smoking. It's hard to stop. Well, thank you for smoking Leb TV Live consistently. Here they have on the plus line, they have a resistor going to ground that I suppose it might be measuring against. But I'm not really sure that that's needed, if that's really what we're doing. Because the minus line doesn't have that. It has a resistor to output. What if I drop a 1K to ground on these things? On one of the lines, anyway. Let's see. That would have been a nice little narrative if this whole thing had just kind of wrapped up and the circuit worked. And I went, whoa, this actually really works, sort of. We don't get that around here very often. So the one on the positive line has a resistor to ground from its output. These both actually, well, those are isolated and these aren't. So this would be like putting a resistor to ground right here. If I did that, does my circuit light up like a Christmas tree? No. Or it would be on the output, wouldn't it? So this would go here, and it would go to ground. Ground. It feels like something wants to happen. I can see those the little nubs moving around. Let's try it on the other end here. Wait, that's wrong. Am I? No, I'm hooked up to the right thing. Oh, I'm not hooked up to the output. Wait a minute. No, that's the positive. Oh, look at the positive input. It's a square wave. What the heck? Whoa! Well, that might mean it's valid input. And then this would be output all the way down here. And if we have a resistor to measure across, it becomes indecipherable. What I really wanted to see out of this thing was opposing waves. where one goes in one direction, the other goes in the other. What I got, nothing like that. My arms are beaten. I spent 2 hours in Beat Saber after work today. That's good exercise. You gotta add weights to it, and then you'll start really killing people. These are unfortunately sucking down quite a bit of current. They're using like 10 milliamps each. So I don't know. I gotta figure out how to use these 10K pots to control this thing with much smaller voltages. But in the end, I hooked everything up, and it appears as though something ain't right. Something's not quite happening the way it should happen. Do I need a resistor across the output? I don't think so. I think those are just for current limiting purposes. I mean, we're essentially making a voltage divider out of one of them in this circuit. But those aren't powered off at 12 volts. I don't know what the OPA 4134 is doing. 200 grams of weight on each controller. Damn. I could do more, but I don't want to lift the weight. I just want to move. Yeah, it's good to get moving a little bit. Watching Beat Saber is so much different from playing it. I don't think I've played Beat Saber much, but watching somebody play it, they look like they're doing just the most cerebral thing ever. They're like, boo, ba, 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 ba. They know everything, all the moves and all that stuff. And you're like, how do they know to do that? It's got to be so different actually playing the game than it is to just watch somebody play it. They look like they are super galaxy brain gamer moves. Although I guess the same thing kind of applies to like DDR and stuff like that too. Single-ended input with non-inverting gain of 2 volt per volt. This is just from a design application from a... Wait, is that from the same thing? Oh, this is the slightly different... No, this is the same data sheet. I guess I have it open twice. Why do it do like this? Why are? What going on? Yeah, it's the muscle memory. It's the same thing with stuff like a spinning poi or like learning a skateboard trick where you try and try and try again and try again and try again. And when you complete it once successfully, take a break. You just take a break. You just walk away from it. Don't think about it. Don't obsess. You've got to be cool. You got to be cool about it. Be cool, man. You don't want to scare away any of the muscle memory. And then you come back to it a couple moments later, and all of a sudden you can do it perfectly every time. It's just one of those things. So Hajiwa's getting the voltage control level. How do you know to do this? This is crazy. Attenuation, offset. How do you know to do this? 10K with a 2.2K, but that's on the output of the whatever signal you're sending into. CV or 0 to 12 volt with a 10K on there, mixing it in. So whatever's coming out of here, oh God, I can't do this in my head. Input going into its own amplifier, it's V2164, and then this whole circuit is based on, I don't know, it's based on something else. Mutable instruments fails. Of course! Everything leads back to the same. It does not use a constant voltage diode like the LM4040B10 uses in Veils. Instead, it uses a semi-fixed resistor for adjustment. So that would be these two, I guess, instead of a negative 10 volt source. What Mutable typically will do is take your plus minus volt signal, mix it in with negative 10 volts. And what that does is it shifts it to the negative space of plus minus 10 volts. You can think of plus minus 10 volts with a ground in the center as instead being zero, you can instead shift it. You can think of it as ground, 10 volts, 20 volts. If you mix it with negative 10 volts, you're offsetting it by negative 10. And so plus minus 10 volts becomes 0 to negative 20. And then you take a third of that, and your plus minus 10 volts becomes 0 to positive, because it's an inverting amplifier, 3.3 volts. And so you can double layer that with an op amp that only functions up to 3 volts, 3.3 volts. And then you basically have a safety shifting circuit for control voltages coming into your synthesizer. So if you come into a 3.3 volt digital circuit, you can limit that op amp won't be able to go into voltages that blow up your system. Because on its input, it can take the input, but it can only output up to what it's being given in terms of VCC. So that's how you safety your sensitive digital electronics from an incoming control voltage that can go well out of spec. 0 to 10 volts is all well and good. That's what the negative 10 volt source is doing. It's doing the shifting for you into negative space so your amplifier can flip it into positive space and have that control output. You can do the same thing with audio. You can do a bunch of different stuff with that sort of shifting scheme. And that's what Mutable Instruments loves to do. It's what I've implemented in a lot of my circuits, but Hajiwo is not doing that. Instead, he chooses to have some kind of a 12 volt to ground shift going on with this. So it's a strange thing. I don't know what precisely could be going on here, but it's going into an inverting amplifier, and then it gets inverted again through the transconductance amplifier, and then turned back into a regular signal over here with a 490 ohm resistor on the output. So he's got 100 kilo ohm feedback, or whatever that is. There's a whole thing about transconductance that I need to read up, about the turning it into voltages. I don't think that output resistor is there for anything except for protection. I don't think it's like an impedance thing, is it? DDR is a bit hard for me. My leg just gives up, and then it's not really made wheelchair friendly. Yeah, DDR, you definitely need like stomping. Could you put like DDR on the ceiling? That would be. Hey, we could do floor and ceiling DDR for just the weirdest body movements possible. But yeah, Beat Saber seems like it's a lot of fun. I need to dig out the we saw that earlier today. I showed that wall, and on the wall is my VR headset, and it works amazingly well with my new computer, but I haven't gotten that much time in doing VR stuff. We've been very busy this year. So yeah, I love Hajiwo's circuits. He definitely does a great job of boiling everything down into very simplistic, simple terms that we can kind of wrap our brains around very nicely. This thing, however, is kind of cursed. I don't know what's going on with this thing. It seems like we're adding back in an offset voltage using one of the V2164s in order to make sort of a logarithmic thing out of it, I guess. Our CV and our offset are coming in there positive, getting inverted, and then going into the V2164. I don't understand why or how that works. And maybe I need to bypass the transconductance amplifier so that we can actually see whether or not this thing is producing proper stuff. Let's try bypassing the 2164. So turn this off. We're going to try this quickly before I have to adjourn. My puppy dog went to the groomers today, so she's like super clean, and I want to go say hi to her. But if our signal's coming in and getting mixed, and it's coming out here and it's going to this amplifier, let's just take this and route it to an output. So we'll put it to the one that's configured like the other transconductance amplifiers. That's this one right here. This one has the negative line going to ground, and it has the positive going to feedback. And the signal input's coming from here. So we can take, what are we doing? We're taking this one out, and I'm going to get this signal, because we've got something coming into here, which goes to this one. This one here, we take this output, and we route it, and I guess I could route it from here. We route it over to here on the positive input. Okay, jeez, that was more complicated than it needed to be. Whatever else is connected to that output, this one is connected to it right here. It's a bit of a jump. It's got to kind of travel a little bit to get to where it needs to go, but we'll put that all the way to the positive, the plus input over here, like that. So now we've bypassed one stage of the amplification, and we are putting a transconductance amplifier on the other part. So, I don't think I turned anything off for that. Oh, yeah, I did. Okay. Turn the output on. Turn the radio on. And then nothing happens. Try to adjust things so that I can at least see something. There was a little something right there. Oh, but that's just from crosstalk. Drops off there. There it seems to almost do its job. So why is it having so much trouble? Man, this is very disappointing. Why is that one affecting the other one? That's weird. Well, how is it connected in our original circuit, in our datasheet circuit? More complicated than it needs to be, give you more Rube Goldberg points. I think a lot of the complication is for corner cases of like, oh, we found out that this happens if you treat it a particular way. It's like if you do a full engineering like breakdown of a design, then you run into more of these weird problems that you need to filter out with things like capacitors. Because we've got this going on. We've got the 30K and the 510 going into the amplifier. And then that comes out, and we are just basically hitting a circuit like this. Let me check the inverting one, because the inverting one kind of worked a little better. So if I unplug what I just plugged in, I'll turn the power off. I'll be a little bit nice and at least just turn stuff off in between tests. Let's get this out of here. What I'm doing is I'm just hooking up to the output from the first filter stage right here, for the first amplifier stage. So I got to go from here. I need to go to here, and without this wire in there. This one goes away. Give me that out, and then go. We'll just use a big wire for this, just so I know I'm hitting the right stuff. Actually, I'll just use a vertical jumper. Vertical jumpers have their place in the garbage. No, they're fine. They're fine. They sometimes come in handy. So we just go from meow to the inverting amplifier input, and that is referenced off of ground. So this is as simple as it gets, right? This should just work. Chuck. No, you gotta salt bay the caps in when you're done designing everything. When you're done the design, you just gotta sprinkle it with caps. So we are looking at this amplifier. It does nothing. Cool. I said that on stream at one point, the Salt Bay with caps thing, and then like a day later, I see it in meme form on the internet. Still feel like somebody stole my joke. Where are my voltages? What's going on here? Where are you? You're supposed to be outputting stuff. What the heck? What did I do? Huh? What did I do? Like, I'm speechless. What's going on here? Did I lose my ground connection? No, I still got ground. It's all the way over there. What if we poke in on this signal? Uh-huh. Over here? That should just look like the same wave. Why does that not look like the same wave? Do I have a 1 to 10? What's going on here? That's on 1x. This one's on 1x. Both on 1x. Okay, so those are on top of one another. After the filter, it's just dead. Is it a problem with my filter? Yeah, that's what the static electricity caps are like. It's just these little guys that you just kind of sprinkle down on any human input. We have a scope on this. Oh yeah, look at all the space we have now to see what I'm doing. All this room. Look at this. So all right, we're coming in here. Coming in hot. That's exactly on top of the other waveform. And then we go through a 30K that like totally eliminates it. Makes it into this pithy little signal. This little piss signal. I guess that's doing frequency stuff. Is the 30K the problem? But Mutable uses a 49.9 kilo ohm resistor. That is a significantly larger resistor than what we have. And this 30K is what's suggested by the data sheet. It's just, I can't see shit after the 30K. It's like nothing is going on here. And yet we did try this circuit. We tried the circuit out. It looked fine. That's all the way up at 12, so we can't really see that. And then the output from our junctions are here. And the reason that it looks so fucky is because it's actually transconductance. And this voltage level is unimportant to the function of the rest of this thing. And it really does look like there is a signal there. So then the next problem is, why am I not seeing on my amplifier a proper output signal? I'm adjusting the wrong one. So now I've taken one amplifier out of the equation, and we're running it in essentially exactly the configuration that the datasheet calls for, which is somewhere around here. That's this one. So V2160, and there's also the SI 2170 or whatever, the 2164. Sorry, the number is 2164, right? There's a couple different manufacturers of 2164s. The SS2164, slightly different properties, but it's got all these circuits as well all over the place. So we have something like 32K on our feedback resistor. We don't have the capacitor, which means some RF frequencies can get through. Oh well. But what I'm not seeing is like a proper signal coming out of this thing. We have pretty much this circuit right here. I have a 560 PF, I got a 500 ohm, and a 30 kilo ohm going into the appropriate pin, coming out of the appropriate pin, going into an op amp, in our case, a TL074, which works just the same, going between minus and V out. So between, which one is that? It's minus is the closer one. So yeah, minus and V out, going between minus and V out. Here's a signal in, comes from pin, oh, look at that. Pin, well, it's technically pin 13 over here. 13, all the way down to this, all the way over to here. Everybody's connected to 12 volts. We're going in to the 32K amplifier and coming out here. Why don't I see anything? What's going on here? My probes shouldn't be in weird modes. They should be in just a normal old DC mode so that we can see positive and negative voltages. And since this is a transconductance amplifier configuration, I should absolutely be seeing current on the outset. Plus 12 and ground are all connected. Everybody should be happy. We should all be millionaires. But for some reason, I don't get nothing going on over here. Now we're still connected to plus minus. Yep, okay. Check everything. Look at the power supply. What's the current going through? 0.16 and 0.013 and 0.016. So we're taking tens of milliamps, which should be, you know, right on spec. There's nothing controversial about that, except for the fact that this chip gets pretty warm. It's not warm to the touch. It's just warm. It looks warm on the thermals. Probably like 100 degrees Fahrenheit. I'm definitely getting my output for, yeah, see that? It bumps the thing down to like negative 12 or whatever. Now, does one affect the other for some reason? No. I do not understand why I'm striking out on this circuit. Let's try the other one. Try this one. I don't think this one's hooked up to anything. That's nothing. It does nothing. And this is just a frequency sweep. It's like 500 kilohertz to 5,000 or something. That's a little less than that. I think it's 5 to 1,000. It's just like a mid-audio sweep. It's not pushing the envelope in any direction. I don't get it. What did I do? What did I do to deserve this kind of treatment? Well, okay, so not succeeding is also something that can happen in electronics, and I think one of my main things is that my potentiometers adjusting these things are, I don't know, they're like out of spec. I don't know how to get them back into spec. I got to look that up a little bit. I got to actually hunker down and research that. Everything that we hooked up today, the schemes that we have, should work just fine, but they're not. I don't know. My input audio amplitude is something that I've got to kind of research a little bit more. Some people say that audio in modular synthesizer can get up to plus minus 12 volts, which I think is fairly rare to see. So plus minus 10, we're giving it plus minus 5. We should have enough voltage there that we can kind of test stuff. This is another argument for the module testing module project. Unfortunately, I don't have a thing that's going to power up test boards and give them the gates and the voltage per octave and, you know, those kinds of audio signals that I would want to analyze on the other end. That's where that comes in handy. You know, I've done everything in my power to get this circuit together. It's not a difficult circuit. It's not a complicated circuit. The sun's down, so I think I'm done. I need to go take my puppy for an evening walk, touch some grass, and get my head straight, and we'll think about what I can do in order to get this thing running again. It's either we do this on Thursday or we work on the module testing module. Both projects are sort of in this nebulous state of pre-design that I need to bring in to sort of their final form. And I think of the module testing module, we just need to hook up a lot of stuff. I need to put that schematic together. There's a lot of stuff that needs to be connected to other stuff. And then we need to start massaging the spider web of parts that are eventually going to go together to make that device. And then when we finally get that board done in 1,000 years and I get it in, I can build it and then put up some rudimentary software to make a module tester that'll temporarily allow me to test a lot of these, you know, the M303s and stuff like that and get them fixed. We've got a lot of work to do. So we're going to come back on Thursday. Wednesday, I'm going to spend my time trying to further these projects, and we'll see where we get to with that. Until then, I urge you guys to go out and move your bodies around if you've been sitting here for a while. Other than that, thank you for joining me. It is cold out. We are hunkering down. We're going to get stuff done. Until Thursday, I will see you guys later. And let me just quickly check who's on first. Well, Davies, if you guys feel like it. Cheddar, I don't. When did I follow them? Oh, I see. Wait, Sir Lar? No, Lauren's doing something else. Paleontologizing is still on. New dinosaur, introducing something or other. Rabaz is farming. All right. Nothing terribly of note. Best of luck. May the electrons ever be in your favor. Yes. It is unfortunately a frustrating day here in the electronic jockeying, I don't know, setup. But we'll get over it. We'll get over it. I'm gonna hunker down. I'm gonna look stuff up. We'll figure out what the heck's going on with this thing and report back. And I will see you guys on Thursday. Thank you for joining me. Usually I do like an end gag, but I don't really have one. So I'm just gonna click on the scene. Oh yeah, it's down here. The technical issues scene. I should